Hello there, and welcome to Just About Earth, where we take strange questions from history, slow them down, look at what the evidence actually says, and try not to become too attached to an explanation before we've examined the stones sitting quietly in front of us. Tonight we're heading high into the Peruvian Andes, into the former heartland of the Inca Empire, where some of the most remarkable stone structures in the ancient world have survived earthquakes, conquest, weather, rebuilding, tourism, and several centuries of people standing beside them wondering exactly how on earth they were made. Our question sounds simple enough at first. Did the Inca use machines or construction methods that we no longer understand? It is the sort of question that can lead very quickly into extraordinary claims, so we're going to take the slower route. We'll look at what is genuinely unusual about the masonry, what archaeologists have been able to reproduce, what remains uncertain, and why enormous stone walls can sometimes make a perfectly sensible explanation feel strangely incomplete. Before we get too comfortable among the megaliths, I'd love to know where you're listening from tonight, and perhaps something else as well. Have you ever visited an ancient place where the physical remains seemed more impressive than the explanation written on the little sign beside them? Maybe it was a castle wall, a pyramid, a Roman road, or simply an old stone bridge that made you wonder how anyone moved that much material without cranes, engines, trucks, electric saws, or someone nearby complaining that the battery had gone flat. There is something useful about that reaction. Wonder is not evidence, of course, but it can be the beginning of a good question. And if you enjoy these quiet investigations into archaeology, engineering, history, and the occasional mystery that refuses to fit neatly into a display cabinet, you can give the video a like and subscribe to the channel. It helps this little corner of curiosity reach other people who enjoy difficult questions without needing the answer to involve either extraterrestrials or a prehistoric gentleman carrying a laser cutter. The Inca themselves hardly need technological exaggeration to be impressive. By the time the Spanish entered their empire in the 16th century, the Inca had created the largest state in the pre-Columbian Americas, administering communities across an enormous and difficult landscape of mountains, deserts, plateaus, valleys, and forests. Their engineers built roads over high passes, terraces across steep slopes, drainage systems, storehouses, bridges, ceremonial centres, settlements, and agricultural infrastructure without horses, oxen, iron tools, or wheeled vehicles being used for the heavy transport systems familiar in Europe. Machu Picchu alone contains roughly 200 structures arranged across a steep mountain ridge and integrated with terraces, water management, and the surrounding landscape. UNESCO identifies it as a 15th century Inca creation and one of the major surviving achievements of the civilization. Yet even after acknowledging all of that, certain pieces of Inca masonry still create a very particular kind of confusion. Visit Sacsayhuamán above Cusco, and you encounter long defensive or ceremonial terraces made from irregular polygonal blocks, some of them enormous. Travel into the sacred valley to Ollantaytambo, and you find massive worked stones, unfinished blocks, quarries, ramps, walls, and architectural details that preserve evidence of construction at different stages. Go on to Machu Picchu, and you see another range of techniques, from comparatively ordinary stone walls to carefully dressed masonry in important buildings. There is no single thing called Inca stonework, in the sense of one method applied everywhere. The workmanship varies according to place, material, function, and importance, which is actually one of the first clues that we are dealing not with a mysterious universal machine, but with a sophisticated building tradition capable of using several different approaches. What attracts the most attention, however, is polygonal masonry. Instead of cutting every block into a standard rectangle and stacking the stones in regular courses, builders shaped irregular blocks so that they fitted against several neighbouring stones at once. One block might have 5 visible sides, another 8, another 10 or more. The joints bend, turn, rise, fall, and sometimes wrap around corners. In photographs, the wall can look almost like a giant stone jigsaw puzzle, except no helpful manufacturer printed a picture on the box and some of the pieces weigh more than a delivery van. There is also no mortar filling the visible joints in the finest examples. The stones support and constrain one another through their shapes, their contact surfaces, their mass, and the overall structure of the wall. This is where the phrase, "they fitted stones together," becomes a little misleading, because it makes the process sound like arranging furniture. A polygonal wall is a three-dimensional fitting problem. Shape one face of a stone and you affect the way another stone can meet it. Change a corner and you may alter the contact with the block above. Remove too much material and you cannot simply put it back. The difficulty increases as the stones become larger, because checking the fit is no longer a matter of lifting the piece, looking underneath, shaving off a small bump and trying again. When a block weighs several tons, every movement requires preparation. When it weighs tens of tons, the problem becomes an exercise in logistics before the shaping even begins. This is part of the reason alternative explanations have become so popular. People look at the joints and imagine mechanical saws. They look at smooth depressions and imagine powered grinders. They see small holes or grooves and wonder about drills. Rounded surfaces suggest moulding. Oddly shaped projections are interpreted as lifting points. Some viewers go further and suggest chemical treatments that soften stone, allowing builders to shape it almost like clay before it hardened again. The attraction is understandable. We tend to explain unfamiliar workmanship through familiar technology, and today the easiest way to produce a smooth stone surface is usually to use a machine. It therefore feels natural to assume that a smooth ancient surface must also have required something machine-like. The problem is that appearance alone cannot tell us what tool created a surface. A modern power grinder leaves a smooth result, but so can repeated abrasion. A powered saw produces a straight line, but patient manual work can also produce one. Curves that look moulded can be made by pounding and grinding. Ancient craftspeople regularly achieved surfaces that seem surprisingly modern, because we underestimate what happens when skilled labour is applied repeatedly to the same material. The modern mind tends to ask, what tool would let me finish this quickly? Ancient monumental construction may have operated under a very different question. How many workers, how much skill, and how much time can we devote to making this important structure exactly the way we want it? One of the most important attempts to answer that experimentally came from architectural historian Jean-Pierre Protzen, who studied Inca quarrying and stone cutting in detail, particularly around Ollantaytambo. Protzen examined quarries, unfinished blocks, completed walls and likely working traces, then experimented with tools consistent with archaeological evidence. He concluded that surprisingly simple methods could accomplish much of what had sometimes been treated as inexplicable. Large hammerstones could be used for splitting and rough work, smaller hammerstones for dressing surfaces, and repeated fitting could gradually bring neighbouring stones into close contact. His research argued that stones already placed in a wall could be adjusted to receive the next block through a careful trial and error process. That is a significant piece of evidence, because it moves the discussion away from what seems possible while looking at a photograph and toward what actually happens when someone takes the proposed tools and strikes the proposed stone. It demonstrates something that is easy to forget. Stone does not have to be sliced like bread. It can be pecked, fractured, crushed, ground, abraded, and progressively reshaped. Thousands upon thousands of controlled impacts can turn an irregular surface into a planned one. To a person watching the first 10 minutes, almost nothing appears to happen. To a team of specialists working over a long period, quite a lot can happen. Stone is stubborn, but human beings have the rather useful ability to be stubborn for longer. Still, demonstrating that hammerstones can shape rock is not the same as reconstructing every construction sequence at every site. This distinction matters. Experimental archaeology can establish that a proposed technique works, can produce recognizable marks, and can achieve particular results. It may not tell us exactly how many workers were involved, how templates were used, how fits were checked on the largest blocks. what abrasives may have supplemented pounding, what specialist tools have failed to survive, or how individual building crews organise the entire process. There is a large difference between saying that known methods are capable of producing sophisticated masonry and saying that we possess a complete instruction manual for Sacsayhuamán. We do not. The same caution should apply in the opposite direction. A gap in our reconstruction is not evidence of a lost machine. Archaeology is full of incomplete processes because wooden tools decay, fibres disappear, ropes rot, temporary ramps are dismantled, workshops are cleared, metal objects are recycled, and knowledge that once existed in people's hands is not necessarily recorded in writing. A specialist stonemason may know dozens of small techniques that would never occur to someone who merely owns a hammer. The angle of a strike, the selection of a hammerstone, the order in which surfaces are worked, the way a block is supported, the use of marking compounds or checking methods, the recognition of natural fractures in the rock, and the decision to stop before a corner breaks away can make the difference between skilled work and an afternoon spent creating expensive gravel. There is also a linguistic trap hidden inside the word machine. We often imagine a machine as something with metal gears, an engine, a spinning blade, perhaps an electrical cable stretched inconveniently across the floor. But technically, simple machines include levers, inclined planes, wedges, and arrangements that multiply human force. Ancient builders did not need an industrial machine shop to use mechanical principles. Ropes, wooden levers, prepared ramps, rollers in appropriate circumstances, sledges, cribbing, wedges, and coordinated pulling systems can move surprisingly large loads. The question therefore becomes more precise when we ask not whether the Inca used machines, but whether they possessed powered cutting or shaping technology significantly beyond what archaeology currently attributes to them. At present, there is no accepted archaeological evidence for electrically powered saws, high-speed drills, advanced metal cutting machines, or some forgotten industrial system operating in the Inca world. No motors have been excavated. No machine workshops have been identified, no power sources emerged, no collection of anomalous cutting blades has appeared from a sealed Inca context. That may sound obvious, but it matters because a technology capable of shaping huge quantities of hard stone mechanically would normally be expected to leave more than smooth walls behind. Machines require materials, maintenance, tools, spare components, workshops, operators, and usually characteristic waste. The larger the proposed technology, the larger the archaeological footprint we should expect. The stone softening idea faces a similar difficulty. There are Andean traditions and modern claims involving plants, acids, mineral treatments, or chemical processes supposedly capable of changing stone surfaces, and these stories are extremely popular online. The dramatic version imagines enormous blocks being softened until they could be pressed together like modelling clay. Yet the physical evidence needed to establish such a process has not been demonstrated for the famous Inca walls. If a chemical method altered the mineral structure of the stone substantially, we would expect laboratory analysis to reveal differences between treated surfaces and untreated interiors. Until such evidence appears, the stones look softened remains an observation about appearance, not proof of a forgotten chemistry. What makes the subject worth investigating is that the ordinary explanation is itself extraordinary enough. Imagine selecting a suitable boulder, separating material from a quarry, roughing out the intended block, moving it across difficult terrain, raising it toward a construction platform, shaping several contact surfaces, checking those surfaces against neighbouring stones, making corrections, and finally placing the block so that its weight contributes to a stable wall. Now imagine doing this repeatedly, not for a decorative garden feature, but for monumental architecture commissioned by an empire. Even without a lost machine, there is clearly lost knowledge here in the broadest sense. We do not possess the lived expertise of the people who supervise that work, We have evidence of their methods, but the craft tradition itself was disrupted. The Spanish conquest changed the political and economic system that made imperial construction possible. Large-scale Inca building programs depended on state organization, specialist knowledge, tribute obligations, labor mobilization, administrative control, and cultural priorities that did not continue unchanged under colonial rule. Once the system supporting monumental masonry disappeared, there was no reason to expect every technique within it to be passed down intact for centuries. A skill can vanish without the tool being mysterious. There are crafts from much more recent history that modern people struggle to reproduce efficiently because the specialists, routines, supply chains, and accumulated practical habits are gone. That is an important possibility for us to keep in mind. Lost technology does not necessarily mean a lost device. Sometimes the technology is a process. Sometimes it is knowing exactly where to strike a stone. Sometimes it is understanding how to read a fracture line. Sometimes it is a system for transferring an irregular shape from one surface to another. Sometimes it is simply a workforce trained from youth to do something that a modern observer has never attempted. Give an experienced traditional craftsperson a simple tool, and they may produce something that looks impossible to an inexperienced person holding a far more advanced one. Then we come to another claim that complicates the story considerably. Perhaps the Inca did not build all of the most sophisticated masonry attributed to them. According to this idea, some megalithic structures were already ancient when the Inca arrived, and the empire inherited them, repaired them, built upon them, or adopted the sites for its own purposes. This argument often begins with visible differences in masonry. At several Andean locations, finely fitted lower walls sit beneath rougher later construction. To some observers, that seems to show two completely different civilizations, with an advanced earlier culture producing the lower stonework and the Inca adding less sophisticated walls on top. There is a real archaeological principle hidden inside that observation. Buildings do have phases. Later societies reuse earlier foundations constantly. The Inca themselves expanded into regions with long histories and interacted with cultural traditions that preceded their empire by centuries or millennia. Tiwanaku, Wari, and numerous regional societies existed long before the final expansion of the Inca state. It would therefore be absurd to assume that every important idea in Andean engineering appeared suddenly with the Inca and had no ancestry. Civilizations inherit techniques just as they inherit roads, sacred places, agricultural landscapes, political ideas, and occasionally someone else's very inconvenient retaining wall. But visible differences in masonry cannot, by themselves, establish that one wall was made by a forgotten, technologically superior civilization. Different construction qualities can appear within the same culture, because buildings have different functions and budgets. A ceremonial doorway may receive extraordinary finishing while an enclosure 20 meters away is built quickly. An imperial project may employ elite specialists for one portion and ordinary labour for another. Repairs after earthquakes may be rougher than original work. Colonial builders may reuse older stones. Modern restoration can complicate things further. Before declaring that two masonry styles require two unknown civilizations, archaeologists look for stratigraphy, datable material, construction relationships, tool marks, quarry evidence, settlement history, ceramics, historical records, and broader patterns across multiple sites. That broader evidence is one reason mainstream archaeology continues to attribute the famous imperial works at places such as Ollantaytambo and Machu Picchu to the Inca, rather than to an unidentified machine-using predecessor. Ollantaytambo is particularly valuable because it preserves not merely finished architecture, but evidence connected with quarrying, transport, and unfinished construction. Protson's long study of the site focused precisely on these relationships between quarry sources, blocks left in transit, working methods, architecture, and planning. When a site contains both the beautiful finished wall and the less glamorous evidence of how construction progressed, the unfinished pieces are often more informative than the impressive ones. A perfect joint encourages speculation. An abandoned block beside a transport route begins to tell you what the builders were actually doing. There is another reason these stones can be misleading in photographs. A camera removes effort. You see the finished block instantly. You do not see the quarrying, the rejected stones, the broken tools, the workers carrying smaller material, the preparation of ramps, the days spent removing a few centimetres from a stubborn surface, or the repeated checking required before placement. The photograph compresses a long manufacturing process into one mysterious object. We do the same thing with medieval cathedrals, Roman aqueducts, Egyptian sculpture, and old wooden ships. The finished object remains, the thousands of ordinary actions that created it disappear. After enough time has passed, patience begins to look like magic. None of this means we should stop asking whether additional tools or methods were used. Archaeology advances precisely because people question incomplete explanations. Perhaps organic tools remain underappreciated because they rarely survive. Perhaps particular abrasives were more important than we currently realise. Perhaps specialised measuring or templating procedures made irregular fitting far more efficient. Perhaps techniques differed significantly from one building crew to another. Future microscopic analysis of working traces, geological studies of quarry sources, residue analysis, three-dimensional scanning, experimental masonry projects, and better reconstruction of transport systems may refine the picture considerably. There is plenty of room between we know everything, and they had machines more advanced than ours, and that middle ground is usually where archaeology becomes most interesting. It is also where we need to separate three different questions that are often mixed together. The first is whether the Inca could shape hard stone using the tools known from archaeology. Experimental work strongly suggests that they could. The second is whether archaeologists have reconstructed every technique responsible for every unusual detail at every major site. They have not. The third is whether the remaining uncertainties require a lost advanced mechanical technology or an unknown earlier builder civilization. That has not been demonstrated. Keeping those three questions separate allows us to remain curious without turning uncertainty into proof, and there is certainly enough uncertainty to keep us occupied. We still have to look closely at how enormous blocks were manoeuvred, why particular wall styles were chosen, how builders transferred complicated shapes between neighbouring stones, what some unusual surface features actually represent, and whether the frequently repeated claims about impossible tolerances survive close inspection. We also need to ask a question that gets overlooked whenever attention settles on the visible face of a wall. What does the stone look like behind that face? A joint that appears astonishingly precise from the front does not necessarily maintain the same contact geometry through the entire thickness of the block. Understanding how stones actually meet inside a wall can change our idea of what the builders needed to accomplish. So rather than beginning with a machine and searching for marks that resemble its work, we'll begin with the construction itself. We'll look at the stones, the geology, the unfinished evidence, the practical problems, and the methods researchers have tested. Some details will turn out to be less mysterious than they first appear. Others will remain genuinely difficult, and a few may tell us more about the limits of modern assumptions than about any vanished technology. The best place to start is above Cusco, where enormous limestone blocks rise in three great zigzagging terraces, and where the scale of the masonry makes every simple explanation feel just a little less simple once you're standing beside it. At Sacsayhuamán, the question stops being theoretical, because there the stones are large enough, irregular enough, and carefully fitted enough that we can begin asking exactly what a builder would have had to do from the moment a block was selected to the moment it finally became part of the wall. Sacsayhuamán sits on the high ground immediately above Cusco, and from a distance the site can look almost straightforward. There are terraces, open spaces, surviving walls, foundations, and the remains of structures spread across a broad archaeological landscape. Walk toward the 3 famous zigzag walls, however, and the scale changes the problem very quickly. The lower courses contain limestone blocks several meters high, many with irregular polygonal outlines, and some have been estimated at more than 100 tons. Instead of being arranged as neat rectangles, the stones meet one another along angled, stepped, curved, and sometimes surprisingly complicated joints. The wall does not look as though builders first manufactured a collection of standard blocks and then decided where to put them. It looks as though almost every large stone became its own separate engineering problem. Sacsayhuamán is generally associated with the imperial Inca rebuilding of Cusco in the 15th century, particularly the reign of Pachacuti and his successors, although the broader site had earlier occupation and a more complicated history than a single building campaign. Peru's cultural authorities describe the archaeological park as a major sacred and political centre that reached its greatest development during the Inca period, while modern summaries of the archaeology likewise place the monumental stone construction within imperial Inca activity. It is often called a fortress, and there are good reasons for that name. The zigzag layout creates a formidable barrier. The position dominates approaches to Cusco, and Sacsayhuamán played a military role during the conflict that followed the Spanish conquest. But calling it only a fortress probably makes the site simpler than it really was. The complex also had ceremonial importance. Religious architecture, water systems, open gathering areas, terraces, and structures that no longer survive in their original form. Peru's regional cultural authority describes Sacsayhuamán as a major Inca temple complex and emphasizes its ritual roads and hydraulic engineering, as well as its political importance. That matters because the enormous investment in the masonry was not necessarily driven by defense alone. These walls were also part of an imperial landscape where architecture demonstrated organization, sacred authority, and control over labor. A wall made from stones the size of small houses is difficult to ignore, which was presumably part of the point. The first puzzle is the geometry. Most modern masonry tries to reduce complexity. Bricks are standardized because standardized objects are easy to manufacture, calculate, transport, replace, and stack. Rectangular stone blocks work for much the same reason. If every stone has straight horizontal and vertical edges, one template can be repeated thousands of times. Sacsayhuamán takes almost the opposite approach. A large block may contact several neighbouring stones through joints that change direction repeatedly. One side can slope inward, another can turn around a corner, and the upper surface can be prepared to receive 2 or 3 blocks with different shapes. The result is stable, but it requires each stone to be fitted within a local network of other stones. There is no universal mould that solves the whole wall. Imagine trying to reproduce one section using blocks small enough to lift by hand. You place the first irregular stone on the ground. Then you bring another one beside it. Their surfaces do not match, so material has to be removed from one or both. You check the fit, find the high points, remove more material, and check again. Eventually the joint closes. Then a third stone is added above them, but now its underside must match the contours of 2 blocks at the same time. Every correction risks opening another part of the joint. With small stones, this would already require patience. With blocks weighing many tons, the checking process becomes a logistics problem as well as a stoneworking problem. A 12-ton stone does not become annoyed when you ask it to move again, but everyone attached to the ropes probably does. This is one reason Sacsayhuamán is so often presented as evidence of unknown technology. The finished wall hides the manufacturing process. A visitor sees a large irregular block resting beside another large irregular block, with a tight joint between them, but the hundreds or thousands of individual actions required to create that result are invisible. We naturally imagine the fastest tool familiar to us. A powered saw could cut stone, a grinder could smooth it, a crane could lift it. A digital scanner could record the neighbouring shape. Since those are the methods a modern workshop might choose, a wall that looks highly accurate can start to seem like evidence that ancient builders possessed ancient versions of the same machines. There is an immediate problem with that line of reasoning. A finished shape does not identify the tool that made it. A curved surface can be produced by a rotating machine, but it can also be created by repeated impact and abrasion. A flat face can be sawn, but it can also be pounded and ground. A narrow joint can be produced by measuring both stones independently to very high accuracy, or it can be produced by continually modifying one stone to match the other. Those are very different procedures. One requires a precise predetermined design for both surfaces. The other allows the fit itself to become the template. Jean-Pierre Protsen's experimental work on Inca quarrying and stone cutting is important here, because he tested the second possibility directly. After examining quarry evidence, unfinished blocks, working traces, and finished masonry, Protsen argued that Inca builders could accomplish much of their stone shaping with surprisingly simple equipment. Large hammerstones could be used to split and rough out blocks, while smaller hammerstones could dress the surfaces through repeated pounding. His reconstruction of the fitting process involved working stones already placed in the wall so that they received the next block, followed by repeated check-in and correction. In other words, the builders did not necessarily need to measure a complex three-dimensional joint on one stone and then reproduce its reverse shape perfectly on another before the two ever met. They could create the fit through direct comparison. That sounds less mysterious, but it is not the same as saying it sounds easy. Experimental archaeology shows that simple tools can shape stone. It does not turn the construction of Sacsayhuamán into a weekend project. The difference between possibility and efficiency is important. A hammerstone can remove material, but a monumental wall requires material to be removed in the correct places, at the correct stages, while avoiding fractures that ruin the block. A mason must know how the rock behaves, which parts can safely be struck, what kind of hammerstone works best for a particular task, when to change to finer finishing, and how much contact between stones is actually necessary. We can describe those steps in a sentence because none of us has to spend the afternoon doing them. The surfaces themselves offer clues. Many of the famous blocks are not perfectly smooth in the way a machine-polished countertop is smooth. Their faces contain shallow irregularities, impact-like textures, weathering, repaired areas, and differences in finishing. Some stones have raised projections or small bosses. Others contain recesses or marks that have been interpreted as useful during handling or construction, although it would be too confident to assume that every projection served the same purpose. General studies of Inca architecture note that protruding nodes and indentations occur on blocks and may have helped workers grip or manipulate stones during construction. What matters for our question is that these features do not obviously resemble the output of a standardized industrial process. They look like parts of a stoneworking system in which blocks were handled individually. The visible joints deserve the same careful treatment. Photographs often come with claims that the stones fit so perfectly that not even a sheet of paper, a razor blade, or a needle can pass between them. In some places, the joints really are remarkably tight. But statements about universal microscopic precision are usually stronger than what a photograph can establish. The wall faces have weathered for centuries, stones have shifted, sections have been damaged, and the visible front edge of a joint does not reveal the entire contact surface hidden inside the wall. Two stones can meet very tightly along their exterior edges without being polished into matching shapes across every square centimetre behind that line. This is not a criticism of the masonry. It is simply a more accurate description of the engineering challenge. The Inca needed stable contact, controlled placement, and a convincing visible finish. They did not need to create two laboratory-grade surfaces simply to impress someone carrying a feeler gauge 500 years later. The shape of the walls also matters. The great terraces are not composed of thin decorative facades. The blocks form part of heavy retaining and structural systems, and Inca builders commonly used inward-sloping walls and carefully integrated masonry. The polygonal joints distribute contact in several directions, rather than creating uninterrupted horizontal seams. This is frequently discussed in relation to earthquake resistance. Because the Cusco region is seismically active, and many Inca structures have survived repeated earthquakes, better than later masonry built above or beside them. It would be too simple to claim that one clever joint shape made the walls earthquake-proof, but the combination of large mass, dry construction, wall batter, strong foundations, and interlocking geometry clearly produce structures with considerable resilience. Modern descriptions of Inca architecture consistently identify sloping walls, close stone fitting, and interlocking forms as characteristic features that performed well in a seismic environment. Then comes the problem of moving the blocks. The Inca did not use draft horses or oxen for this work, and there is no evidence that wheeled wagons served as the heavy transport system for these monumental stones. Human labour therefore carried most of the mechanical burden, assisted by ropes, levers, prepared routes, ramps, poles, and careful organisation. Historical and archaeological reconstructions describe large labour forces mobilised under the Inca state, with quarrying, transport, foundation work and masonry distributed among organised groups. Some later accounts give very large workforce numbers for Sacsayhuamán. The exact figures should be treated cautiously, because colonial chronicles are not engineering payroll records, but the broader point is secure. Imperial construction relied on the state's ability to mobilise substantial numbers of workers. Moving a large stone with ropes is not mysterious in principle. Human beings can combine their force, reduce slopes, build temporary ramps, use levers to shift a load incrementally, and prepare paths to control friction. The mystery lies in the practical details. How thick were the ropes? How were they attached without slipping? How many pulling teams were used? How did supervisors coordinate them? How were stones stopped on slopes? How were they turned? How were they raised into final position without damaging carefully worked edges? These questions are not arguments for advanced machines. They are reminders that dragged with ropes is about as complete an explanation of megalithic transporters crossed the ocean with sails is an explanation of operating a 16th century ship. Correct, certainly, but missing quite a lot of the interesting part. The Inca had exceptionally strong fibre technologies, and ropes were not primitive simply because they were made from plants rather than steel. Large coordinated pulling systems can generate tremendous force. Levers multiply force further, while ramps trade height for distance. None of those methods violates engineering principles. The difficult issue is reconstructing how they were combined at Sacsayhuamán, and how the largest blocks were controlled safely. Temporary construction features are especially hard to recover archaeologically, because ramps can be removed, soil can erode, wooden levers decay, and ropes vanish completely. The wall remains while much of the equipment that placed it disappears. This creates exactly the sort of archaeological silence in which speculation likes to move in and unpack its luggage. An even more important fact is that the Sacsayhuamán we see now is not the Sacsayhuamán the Inca saw. After the Spanish conquest, the complex was extensively dismantled, and stones that could be transported were reused in colonial Cusco. Historical summaries describe the site as having been quarried for building material, leaving a surviving landscape heavily biased toward foundations and blocks that were difficult to remove. That means the giant stones dominate our modern impression partly because they were the least convenient pieces for later builders to steal. Smaller dress stones, upper buildings, towers and architectural elements disappeared in large quantities. The surviving megalithic walls therefore look almost like the skeleton of the site rather than the complete complex. That point also affects claims about construction chronology. Alternative theories sometimes argue that the giant polygonal walls must belong to a much older civilization because later-looking Inca masonry appears smaller or less sophisticated. At first glance, the contrast can be striking. Massive lower blocks may sit beneath smaller masonry, and colonial construction may sit above both. But size differences do not automatically establish different civilizations. Retaining walls need different engineering from houses. Foundations use different blocks from upper stories. Ceremonial architecture receives different labour from ordinary buildings. repair work differs from original construction. Reused stones add another layer of confusion. Archaeologists therefore do not date a wall merely by deciding which stonework looks more impressive. There was certainly life in the Cusco region long before the imperial Inca state. UNESCO notes that Cusco itself developed after more than 3,000 years of pre-Inca occupation, and the Inca inherited a landscape with deep cultural history. The Andes also contained earlier states and stoneworking traditions, including Wari and Tiwanaku, that long predated the height of the Inca Empire. So the broad idea that Inca engineering grew from earlier Andean knowledge is not controversial at all. Technologies rarely appear from nowhere. The much stronger claim is that the main megalithic walls of Sacsayhuamán were inherited intact from an unidentified earlier civilization and merely claimed by the Inca. That proposal requires evidence beyond the fact that the masonry is impressive. Current archaeological interpretation connects the monumental development of the complex strongly with imperial Inca Cusco, even while recognizing earlier occupation and multiple phases within the larger site. This distinction is useful because there is a tendency to create an unnecessary choice. Either every detail of Sacsayhuamán must already be completely understood, or an unknown older civilization with lost machines must have built it. Archaeology rarely gives us choices that are convenient. We can have strong evidence that the Inca were responsible for the monumental project, while still lacking a perfect reconstruction of every working technique. We can reproduce stone pounding experimentally while still debating the most efficient way huge blocks were checked and repositioned. We can identify plausible transport methods without knowing the exact arrangement of every rope and ramp. Incomplete knowledge is normal when the builders left no engineering handbook behind. The idea of stone softening becomes particularly tempting at Sacsayhuamán, because some blocks have rounded edges and slightly bulging faces. To a modern eye, certain joints can look as though one stone had been pressed against another while the material was soft. Yet rounded masonry does not require soft stone. If a builder removes material by repeated pounding rather than slicing it with a rigid saw, rounded transitions are entirely natural. Finishing can exaggerate the effect, and centuries of weathering can change the surface further. To demonstrate actual stone softening, we would need more than a visual resemblance to clay. We would need physical evidence showing that the rock's mineral structure had been chemically or thermally altered as part of construction, together with a plausible method and ideally residues, tools, processing areas, or repeated diagnostic traces. The walls themselves do not currently provide that chain of evidence. Mechanical cutting theories face a similar problem. A powered machine capable of cutting these blocks would not only have to exist, it would have to leave an archaeological footprint. There would need to be components, cutting media, power systems or energy sources, workshops, characteristic tool marks, or some other material evidence indicating a technological system beyond known Inca practice. Without that, a smooth or narrow joint is not enough. We should be open to unknown tools, because organic or recycled equipment can disappear. But the more technologically elaborate a proposed machine becomes, the harder it is to explain why every part of the machine vanished, while thousands of tons of its supposed output remained in plain sight. The most interesting possibility is actually less dramatic and more realistic. Some important techniques may indeed be lost, but they may have been procedural rather than mechanical. Perhaps specialist teams used ways of transferring contours that have not survived in written descriptions. They may have used pigments to mark contact points, temporary supports arranged in ways we have not reconstructed, particular sequences of pounding and grinding, or specialized wooden gauges that decayed centuries ago. There may have been established rules for deciding which stone should go where before detailed fitting began. Experienced quarry workers may have recognized natural shapes that minimize later work. Transport crews may have developed rope systems that were obvious to them and are not obvious to us. None of this requires technology more advanced than the Inca are known to have possessed. It requires something far easier for history to lose: professional experience. That is probably the most useful lesson Sacsayhuamán gives us at this stage. the walls are not evidence that archaeology has no explanation. There are experimentally supported methods for quarrying, pounding, dressing and fitting Inca stone, and there is clear evidence for a political system capable of organising large construction projects. At the same time, the site is too complicated to be reduced to the phrase, "they hit rocks with other rocks." The stones preserve the final result of a complete engineering system involving material selection, quarrying, labour organisation, transport, temporary works, stone dressing, positioning, measurement, fitting, drainage, foundations, and architectural planning. We understand parts of that system very well and other parts less completely. Calling the whole thing impossible understates Inca skill, while pretending every practical detail has been solved understates the archaeological problem. Sacsayhuamán also gives us one final clue that will become more important as we move away from Cusco. Finished architecture can hide its own history. Once a wall is complete, we mainly see what succeeded. Broken stones may be removed, failed attempts disappear into fill, ramps are dismantled, tools are carried elsewhere, quarry scars may be separated from the monument by kilometres of landscape. What we really need is a place where the construction process seems to have stopped before everything was tidied away, leaving unfinished blocks, transport routes, worked stones, quarries, and monumental architecture close enough to compare. For that, the trail leads down from the high ground of Cusco and into the sacred valley, toward Ollantaytambo, where enormous stones were still moving through the construction system when history interrupted the work. Ollantaytambo gives us something that Sacsayhuamán cannot provide quite as clearly. At Sacsayhuamán, we mostly confront the finished result. Huge stones already locked into walls, their quarrying and movement hidden behind centuries of survival. At Ollantaytambo, the building process is spread across the landscape. There are finished walls, unfinished walls, quarries, partially worked blocks, transport routes, ramps, stones abandoned on the journey, and surfaces that seem to preserve different stages of shaping. It is one of those rare archaeological places where the construction site appears to have stopped before everyone had finished cleaning up. That makes it especially useful for our question, because when someone claims that a forgotten machine must have been involved, Ollantaytambo allows us to look not only at the finished stone, but also at what happened before the stone reached the wall. The settlement lies in the sacred valley of the Urubamba, northwest of Cusco, where steep mountains rise sharply above a relatively narrow valley floor. The modern town still preserves important elements of its Inca urban layout, while the archaeological complex includes terraces, ceremonial structures, waterworks, storehouses, residential areas, roads, and the monumental buildings climbing the hillside. Peru's Ministry of Culture identifies surviving structures there with the imperial and late Inca periods, and the wider landscape was linked by Inca roads, irrigation systems, terraces, and settlements that continued to function long after the empire itself disappeared. The place was not simply a fortress, and it was not simply a temple. It was a working imperial centre woven into agriculture, administration, ritual, transport, and the landscape around it. Most visitors, however, eventually climb toward the structure usually called the Temple of the Sun, because that is where Ollantaytambo begins to acquire its reputation for impossible stonework. The best-known surviving feature is the Wall of the Six Monoliths, a row of enormous upright stone slabs separated in places by narrower fitted stones. Their faces are broad, their edges are carefully worked, and the scale makes them feel less like ordinary masonry than sections of cliff that have somehow been persuaded to stand in formation. Scholarly work on Ollantaytambo consistently identifies this wall as one of the site's major ceremonial structures, and the unusual projections visible on its faces have even inspired studies asking whether parts of the architecture had astronomical significance. Looking closely at the wall raises an immediate problem for anyone imagining a simple sequence of rectangular blocks. These monoliths were not quarried a few meters behind the temple and slid gently into position. Their source was at Cachicata, across the Urubamba Valley and several kilometres from the construction area. Protson's field research identified the quarries on the opposite side of the river, high above the valley floor, where large natural rockfalls provided blocks suitable for extraction and working. His broader study of Ollantaytambo was built around exactly these practical questions: where the material came from, how it was quarried, how it was transported, how surfaces were dressed, and how the final stones were fitted and handled. That quarry location makes the wall of the 6 monoliths more interesting than the wall alone. A builder beginning at Cachicata faced a journey that involved moving a massive block away from the quarry area, controlling it down mountainous terrain, crossing or negotiating the river valley, bringing it toward Ollantaytambo, and then hauling it upward again toward the temple complex. At the end of all that, the stone still had to arrive intact enough to be dressed, aligned, and fitted into monumental architecture. Even with perfectly ordinary technology, this is an extraordinary logistical problem. The stone does not care that the emperor has a deadline. Gravity has its own management structure. Fortunately, Ollantaytambo preserves evidence that the Inca did not approach this problem by simply gathering a crowd around a boulder and hoping enthusiasm would overcome geology. Roads, ramps, working areas, and abandoned stones are associated with the quarrying landscape. Large blocks can still be found along the route between the quarries and the construction zones, popularly known as piedras cansadas, or tired stones, because their journey apparently ended before they reached their intended destination. The name is charming, although one suspects the people pulling them were probably more tired than the stones. The existence of these unfinished and abandoned pieces is important, because it links the quarries physically with the building project. We are not guessing at a distant mountain because the stone happens to look similar. The movement of material is written across the landscape. This immediately weakens one popular version of the mystery, which claims that there are no roads or ramps capable of explaining the transport. There are. That does not solve the entire operation, but it changes the question. Instead of asking how a giant stone could possibly have crossed untouched wilderness, we ask how workers used prepared routes to control a giant stone along a difficult journey. The second question is still challenging, but it belongs to engineering rather than magic. Protson's work is especially useful because he did not begin by assuming that Inca stoneworkers possessed some lost cutting system. He examined ancient quarry sites, studied work marks, compared unfinished and finished surfaces, and then tried shaping stone using hammerstones. His experiments led him to argue that blocks could be separated or reduced with larger hammerstones and dressed with smaller ones, while the close fitting between neighbouring stones could be achieved through repeated placement, marking, removal of high points, and adjustment. He described a trial and error process in which already positioned stones could be modified to receive the next block. Ollantaytambo makes that proposal easier to visualise because some of the working traces are still visible. In the Cachicata quarry area, large stone surfaces preserve depressions and trough-like marks associated with material removal. These marks have attracted enormous attention online because they can look like scoops taken from the rock. Seen in photographs without scale or context, they sometimes resemble the marks left by a large rotating cutter or an unknown grinding device. Protson, however, documented repeated patterns of cups, pans and troughs on unfinished blocks, and compared the overall stoneworking process with pounding techniques known from other ancient quarrying traditions. The important point is not that every groove has been explained beyond dispute. It is that similar marks occur in places where the stone was plainly still being worked, giving archaeologists a sequence to study rather than a mysterious groove isolated from its surroundings. This is where visual intuition can become unreliable. Imagine striking the same hard surface repeatedly with a rounded hammerstone. You would not create one clean chisel line. You would gradually crush and bruise a broader area. Continue working beside that area and the depressions begin to merge. Move systematically along a surface and the finished result can become a trough. Someone arriving 500 years later might see the trough, but not the thousands of impacts that created it. A power tool completes the action so quickly that we tend to imagine the shape appearing in one continuous motion. Handworking reaches the same general geometry through accumulation. There are also grooves and narrow recesses in finished architecture that look far more regular than quarry hollows. Some run beside the edges of large blocks, some frame projections or decorative elements. Elsewhere in the complex, channels and recessed forms appear carved directly into stone. These features are often grouped together in alternative explanations, as if every groove must have come from a single unknown tool. But identical-looking geometry does not necessarily indicate an identical purpose. A recess can be decorative, structural, preparatory, unfinished, related to fitting, or part of a larger design that is now missing. Ollantaytambo was modified, damaged, abandoned in parts, and later reused. The temptation is to turn every unexplained mark into a technological signature, when sometimes an unexplained mark is simply an unexplained mark. The wall of the 6 monoliths contains another detail that attracts attention: the narrow stone elements between the larger slabs. From the front, these can give the impression that the wall has been assembled with astonishingly controlled vertical seams. Instead of 2 huge blocks meeting directly along one continuous joint, smaller fitted pieces occupy portions of the gaps. This arrangement makes the wall visually distinctive, but it also shows that the builders were willing to solve difficult joints by introducing additional stones rather than insisting that every giant slab contact the next giant slab perfectly from top to bottom. In other words, the wall itself reveals compromise and adaptation. That is useful evidence because real construction systems usually contain such adjustments. Perfect technologies tend to exist most comfortably in diagrams. The faces of the monoliths create a different question. Some areas are relatively smooth, others are rougher. Projections remain on certain blocks. Portions appear unfinished. If the wall had been produced by a machine capable of rapidly milling stone to exact dimensions, why do different stages of completion remain visible? One possible response is that the construction was interrupted before finishing, which is entirely reasonable. But that explanation also fits manual methods perfectly well. The interruption of Inca imperial building following the upheavals of the Spanish conquest provides a historical context in which major works could have been left incomplete, and Ollantaytambo preserves several signs of unfinished construction. The site's archaeological importance comes partly from precisely this mixture of completed architecture and work left in progress. One of the most revealing things about an unfinished stone is that it tells us what the builders did not need to do. A completed wall can encourage the assumption that every surface was beautifully finished before installation. Unfinished stones show that rough work could occur at the quarry, further work could happen during transport or near the building site, and final finishing might be concentrated only where necessary. This matters enormously when estimating labour. If a block naturally fractured with 2 useful faces, the builders did not need to manufacture those faces from scratch. If most of a rear surface would disappear inside a wall, there was little reason to polish it. If only the visible edge of a joint required fine adjustment, enormous amounts of unnecessary work could be avoided. The builders were not trying to satisfy a modern machinist's definition of precision. They were trying to build an effective Inca structure. That difference is easy to lose whenever someone places a metal straightedge against an ancient wall and announces that the stone is accurate to some tiny fraction of a millimetre. Measurements can certainly be valuable, but the question is what has actually been measured. The visible front edge of a joint is not the same as the entire hidden interface between the stones. Weathered surfaces are not original surfaces. A particularly tight section cannot automatically be generalised across every contact. Claims of extreme tolerances need proper surveys rather than a photograph of someone unsuccessfully inserting a credit card between 2 blocks. None of this reduces the accomplishment. The real engineering remains impressive without microscopic exaggeration. The builders still had to create a wall that looked deliberate, survived under enormous loads, and incorporated blocks whose individual masses made mistakes expensive. If a stone were damaged badly near the end of the journey from Cachicarta, replacing it would involve much more than walking back to the hardware store. The movement problem also deserves a little patience, because this is where discussions often jump from difficult to impossible. Large stones can be dragged. We know this from many cultures and from modern experiments. The force required depends on the weight of the load, the slope, the friction beneath it, and how the pulling force is applied. Reduce friction and the required force falls. Improve the road and the operation becomes safer. Add enough workers and the available pulling force rises. Use levers and small movements become controllable. Build ramps with moderate gradients and an impossible-looking vertical climb becomes a much longer horizontal pull. The challenge at Ollantaytambo is coordination. Hundreds of people do not automatically behave like one enormous muscle. Ropes need to be arranged so workers can pull without interfering with one another. Commands need to be transmitted. The stone must not rotate unexpectedly. If it begins sliding backward, some system must arrest it. When the route turns, pulling directions must change. When the block approaches its final position, brute force becomes less useful and fine control becomes more important. This is where the Inca state itself becomes part of the technology. A society capable of organizing labor, supplying workers, building roads, maintaining storehouses, feeding crews, managing specialists, and coordinating large public works possesses an engineering resource that does not appear in a museum case. We tend to look for the missing device because devices are easy to imagine. The missing organization is harder to see. 1,000 coordinated workers can be a machine. Not in the modern mechanical sense, of course, but in the practical sense of converting organized human energy into controlled work. The Inca Empire was exceptionally good at mobilizing labor for roads, terraces, state facilities, agriculture, and monumental construction. The stone itself records the result, while the administrative system that made the result possible has largely vanished. There is still the river. This tends to appear in documentaries with suitably dramatic music, because the quarry and temple lie on opposite sides of the valley, meaning the blocks somehow had to negotiate the Urubamba. The exact arrangements used for the largest stones remain debated, and this is one area where caution is appropriate. Seasonal changes in river level, temporary diversions, prepared crossings, bridges used for workers rather than stones, and engineered approaches may all have played roles in different operations. We should not pretend to know a specific sequence when the evidence does not preserve it clearly enough, but uncertainty about the exact crossing method does not erase the transport system on either side. The abandoned blocks and routes show that stones were being moved out of the quarry landscape toward Ollantaytambo. Some reached the building site, some did not. The Great Wall exists. Whatever method crossed the valley succeeded often enough to supply monumental construction. The so-called tired stones may actually be among the strongest pieces of evidence against an effortless lost technology. If the Inca possessed a machine that made moving enormous blocks easy, why were some blocks abandoned along the route? Perhaps a hypothetical machine could fail, certainly, but the pattern fits a labour-intensive transport process very naturally. A block might crack, a route might become unusable, a stone might prove unsuitable, political circumstances might change. Construction could halt while material remained in transit. The landscape looks less like the trace of effortless movement and more like the trace of difficult movement that sometimes succeeded and sometimes did not. The quarry evidence tells a similar story. Natural rockfalls were exploited where possible. Fractures in the stone reduced the amount of material that had to be removed. Blocks could be selected partly because they already approximated useful shapes. Protson studies emphasized this practical intelligence. Inca builders were not taking perfectly solid mountains and arbitrarily carving rectangular rooms out of them, one atom at a time. They were reading geological conditions and using the stone's existing structure to reduce labour. That is a form of technology we often underestimate because there is nothing futuristic about it. Knowing which block not to quarry can be as useful as owning a stronger tool. Then there are the protrusions, sometimes called bosses or knobs, visible on large blocks at Ollantaytambo and elsewhere in Peru. Their function is debated in particular cases. They may sometimes relate to handling, positioning, unfinished surface dressing, architectural intention, or other purposes. Alternative theories often compare them with similar-looking projections on ancient stonework in Egypt and other parts of the world, suggesting a shared lost construction system. The comparison is visually interesting, but visual similarity alone cannot demonstrate technological connection. Independent builders dealing with the same basic problem of moving and finishing stone can arrive at similar intermediate forms. A projection left deliberately during rough dressing could be removed later, retained for handling, or incorporated into the final design. Without direct evidence of its use, the sensible position is neither we know exactly what every knob did, nor therefore it was part of an unknown machine. The most dramatic lost technology arguments return to the smooth surfaces. Some photographs of Ollantaytambo show concave areas, rounded corners, or depressions that appear almost melted. This has encouraged the idea that the Inca, or an earlier civilization, possessed a chemical technique capable of softening rock. Once softened, the theory goes, huge stones could have been pressed, scraped, or moulded into shape, and then allowed to harden. It is a wonderfully efficient solution to a difficult problem, which is precisely why it requires unusually strong evidence. If large quantities of volcanic rock had been chemically transformed into a plastic state, we would expect measurable changes in mineralogy, microstructure, residues, or weathering behaviour. We would want repeatable laboratory evidence distinguishing treated surfaces from naturally fractured or mechanically worked surfaces. We would want some indication of the substances involved, and ideally archaeological traces of their production. The appearance of softness is not enough. Repeated pounding naturally rounds edges, abrasion creates curves, weathering modifies surfaces. A process that looks laborious when performed by hand can produce surprisingly smooth geometry, given enough repetition. There is a useful test whenever a lost machine theory appears. Ask what the theory explains that the known methods cannot, and then ask what additional evidence the proposed machine should have left behind. A mechanical cutter powerful enough to process dozens of enormous hard stone blocks should leave characteristic cutting traces. Its cutting elements should require materials. Its operation should create waste patterns. Its power source should exist somewhere. Its maintenance should leave tools or workshops. One isolated groove that resembles a modern saw mark is not enough to establish an entire technological system. The situation becomes more interesting when we ask a softer version of the same question. Could the Inca have used mechanical aids or specialized tools that we have not reconstructed fully? Certainly, wooden devices disappear, fiber ropes decay, abrasives wash away, copper or bronze implements can be recycled, temporary timber frames leave little behind, measuring tools can vanish almost completely, construction knowledge can disappear even when the building survives. This means Ollantaytambo may preserve lost technology without preserving lost machinery. The distinction is important. A technique for copying an irregular contour from one block to another would be technology. A reliable method for positioning a massive stone while workers removed high points beneath it would be technology. A rope arrangement that distributed hundreds of pullers efficiently would be technology. A system of pigments or contact marks that showed where two stones touched would be technology. A particular combination of abrasive, water, pounding, and polishing would be technology. None of those requires engines, electricity, or metals unknown to archaeology. And Ollantaytambo strongly suggests that there was a great deal of specialist knowledge involved. The architecture is not uniform. Different areas show different masonry styles and different levels of finish. The famous monoliths were clearly important enough to justify enormous effort, while other walls were built with much less elaborate stonework. The builders therefore understood when precision mattered and when it did not. They were allocating labour strategically rather than blindly polishing every stone in the valley. That may be one of the simplest answers to the question of why some Inca work appears dramatically more advanced than other Inca work. We make the same mistake when comparing a modern courthouse with a storage shed and concluding that the two buildings must belong to civilizations with different technological levels. They may simply have different budgets. Ollantaytambo is especially damaging to the idea that the most sophisticated masonry must automatically predate the Inca, because the site connects monumental construction to an Inca working landscape so closely. The official archaeological park preserves imperial and late Inca structures, while Protson's detailed study links quarrying, transport, cutting, fitting, architectural planning, and construction phases within the same complex. This does not prove that every stone at Ollantaytambo was first worked during one short imperial building campaign. The valley had earlier populations and Andean architecture developed through long traditions, but the evidence does not require us to insert an unknown megalithic civilization simply because the finished masonry is difficult to reproduce casually. There is a much more interesting mystery already available. We know enough to see the outline of the Inca construction system, but not enough to stand beside the wall of the 6 monoliths with a complete set of instructions and confidently rebuild it using only historically appropriate equipment. We can explain quarry selection, we can reproduce pounding, we can identify ramps and transport routes, we can see abandoned blocks, we can reconstruct plausible labour forces, we can understand how repeated fitting produces tight joints. Yet the exact choreography of the largest operations remains partly lost. How was the last few centimetres of a 50-ton block controlled? How did masons check hidden contact surfaces safely? How much fitting occurred before transport and how much afterward? Which protrusions were temporary and which intentional? What combination of pounding and abrasion produced different finishes? How were ropes attached during particular stages? How did crews prevent damage after months of work had already been invested in a stone? Those are not small questions, and admitting that we do not know every answer does not make the known evidence weaker. It makes the builders more interesting. Ollantaytambo leaves us with a construction process caught halfway between explanation and uncertainty. The quarries argue strongly against the need for mysterious stone creation. The roads argue against stones somehow appearing at the temple without transport. The unfinished surfaces show stages of manual working. Experimental archaeology demonstrates that hammerstones can create the kinds of surfaces needed for Inca masonry. Yet the sheer scale of the complete operation reminds us how much practical knowledge can disappear when a craft tradition is broken. The next place changes the problem again. At Ollantaytambo, unfinished work helps expose the method. At Machu Picchu, the builders faced a different challenge, constructing an entire elite settlement on a narrow mountain ridge in a wet, unstable environment where drainage, foundations, quarrying and architecture had to function together. There, the most revealing stones are not always the largest ones, because the real engineering achievement may be hidden underneath the walls we came to admire. Leaving Ollantaytambo behind and following the Urubamba deeper into the mountains changes the nature of the problem again. At Ollantaytambo, unfinished blocks and quarry routes let us watch something of the construction process. At Machu Picchu, the first impression is almost the opposite. The site feels complete. Terraces descend across the ridge, stairways connect different levels, walls rise directly from natural rock, narrow channels carry water through the settlement, and carefully worked buildings occupy spaces that seem far too difficult for anyone sensible to have chosen for a major construction project. It is easy to become distracted by the famous view and forget the basic engineering question. Before the Inca could fit a single attractive stone joint, they had to make an unstable, wet mountain ridge capable of supporting an entire settlement. That problem may tell us more about their abilities than the tightest joint in the place. Machu Picchu stands at roughly 2,400 meters above sea level on a narrow ridge above the Urubamba River. UNESCO describes the sanctuary as a 15th century Inca creation containing around 200 structures arranged within a landscape of steep slopes, terraces, stone buildings, and surrounding mountain forest. The location is visually spectacular now, but from the point of view of a construction manager it has several irritating qualities. The terrain is steep, transportation is difficult, the region receives heavy rainfall, the ground is fractured, and there is very little naturally flat land. The Inca responded by changing the mountain itself. They cut terraces into the slopes, built retaining walls, created level platforms, controlled water, prepared foundations, and integrated natural rock directly into buildings instead of attempting to erase every irregularity from the landscape. This last point is important, because Machu Picchu is sometimes described as though enormous quantities of stone were transported from some mysterious distant quarry and then machined into perfect shapes. In reality, much of the building material was available locally, and the site contains areas interpreted as quarrying and stoneworking zones. The geology itself may have made this easier than it appears. A geoarchaeological study presented through the Geological Society of America mapped dense networks of fractures and faults beneath and around Machu Picchu, and argued that these natural weaknesses broke the local rock into usable blocks and reduced the amount of energy required to separate building stone. The researcher, Raldo Menegat, further proposed that some parts of the settlement follow the orientations of major fracture systems. That interpretation should not be treated as the final word on why every building stands where it does, but the basic geological observation is useful. The Inca were working in a landscape where nature had already fractured much of the stone for them. That changes the image of the construction process considerably. Instead of workers beginning with an untouched mountain and cutting every block free from solid granite using tiny bronze tools, they could exploit natural cracks, loose blocks, fractured outcrops, and existing planes of weakness. A skilled stoneworker does not ask only how hard the rock is, he asks where it wants to break. Once that principle is understood, a stone that looks impossibly difficult to separate becomes much more cooperative, although probably not cooperative enough to make anyone volunteer for an extra shift. The visible masonry at Machu Picchu varies enormously. Some walls consist of relatively small irregular stones laid in practical construction. Others use rectangular blocks with carefully dressed faces. In the most important ceremonial areas, stones can be fitted closely enough to produce the kind of masonry that now fills documentaries, travel photographs, and enthusiastic internet discussions about lost civilizations. The Temple of the Sun is one obvious example. Its curved wall is built from carefully worked blocks following a rounded plan, something that immediately attracts attention, because producing a controlled curve in stone feels more complicated than producing a straight wall. Other high-status structures contain trapezoidal doors, carefully formed corners, shaped bedrock, and masonry, whose joints are much tighter than those in ordinary buildings nearby. This difference in quality is sometimes presented as evidence that two civilizations built Machu Picchu. The argument usually goes something like this. The finest lower masonry is older and technologically advanced, while the rougher upper masonry belongs to the Inca, who inherited the mysterious structures and built inferior walls on top of them. Photographs can make this argument look persuasive, because there really are dramatic differences in masonry style within the site. The difficulty is that differences in quality do not automatically equal differences in civilization. The same society can build a palace and a storage wall very differently. Even today, nobody visits a marble-lined government building, walks 2 streets to a concrete maintenance shed, and concludes that an unknown superior culture must have constructed the first one. Inca architecture repeatedly shows this selective investment. Important ceremonial or elite buildings received more carefully worked masonry than ordinary structures. Different walls also performed different tasks. A retaining wall holding back a terrace did not require the same visible finish as a sacred enclosure. A foundation stone did not need the same surface treatment as a doorway. Repairs could differ from original construction, and later damage or restoration can complicate appearances further. At Machu Picchu, the variety is therefore evidence that the builders understood where labour was worth spending, not automatically evidence that one group could shape stone while another could not. The more interesting question is how the finest work was achieved. Close-fitting masonry requires careful control, particularly around corners and where multiple stones meet. As we saw at Sacsayhuamán and Ollantaytambo, experimental work by researchers such as Jean-Pierre Protzen has shown that pounding with hard hammerstones can dress difficult stone surprisingly effectively. A large hammerstone removes material aggressively, while smaller tools allow progressively finer control. The surface is not produced in one dramatic cut. It emerges from repeated impacts, checking, correction, and finishing. This method feels inefficient to us because modern construction values speed, but the Inca state could devote large labour forces to structures carrying political and religious importance. Machu Picchu adds another factor that may have made the work considerably more efficient. Many blocks did not have to travel far. Local stone could be quarried, roughly shaped, transported over relatively short distances within the construction zone, and finished where needed. Compare that with Ollantaytambo, where the great monoliths had to descend from quarry areas, cross the valley, and climb toward the temple. At Machu Picchu, the mountain was both building site and source of material. Geological fractures could provide initial block shapes, while construction waste from shaping stone could be reused elsewhere in the site. Nothing says efficient project management quite like turning yesterday's rubble into today's drainage layer. And drainage is where the site begins to look far more sophisticated than photographs of pretty walls usually suggest. Machu Picchu receives close to 2 meters of rainfall in a typical year, according to engineering studies of the site's water management. The terrain is steep enough that uncontrolled water could erode terraces, saturate soil, destabilize retaining walls, undermine foundations, and eventually send very expensive imperial architecture downhill toward the Urubamba. Kenneth Wright, Alfredo Valencia Segarra, and William Laura studied the site's drainage infrastructure and concluded that the Inca developed an extensive system of surface and subsurface drainage suited to these conditions. Their work describes drainage channels, carefully constructed terraces, permeable layers, and systems intended to remove water before it could accumulate dangerously. This hidden engineering is easy to miss because visitors naturally look at walls rather than the soil underneath their feet. Excavation and engineering studies found that terraces were not simply piles of dirt held behind attractive stone facades. They contained layers that helped water move downward and away, including coarse stone and gravel beneath finer soil in studied areas. The terraces therefore performed several jobs at once. They created usable land, stabilized slopes, reduced erosion, and helped manage rainfall. Wright's work on Machu Picchu emphasizes that site preparation, foundations, and drainage were central to the settlement's long-term survival. That is worth pausing over because a wall with a tiny joint can look more technologically advanced than a ditch filled with gravel, but the ditch may require the deeper understanding. A stone block does not care if rain falls on it. A mountain foundation certainly does. If the builders had ignored groundwater and runoff, the finest masonry in the world would eventually have been sitting at a slightly lower altitude. Good drainage is not visually dramatic, which may be why lost technology discussions rarely spend much time on it. But successful civil engineering often works that way. The most important system is the one nobody notices because nothing went wrong. The water supply shows similar planning. Studies of Machu Picchu's hydrology identified a spring on the mountain slope that supplied water to the settlement, along with a canal system carrying that water toward a sequence of fountains. Research measuring the spring found seasonal variation, but concluded that its flow could support a substantial resident population. The builders, therefore, had to understand not merely where water appeared, but how to capture it. maintain a usable gradient, deliver it through the settlement, and then make sure the same water did not become a drainage problem afterward. Anyone who has tried to fix a leaking bathroom will understand that supplying water and controlling water are two very different achievements. This broad engineering context helps us evaluate claims that Machu Picchu preserves evidence of advanced machinery. Take the famous smooth surfaces and fitted corners. Some stones appear remarkably flat. Others incorporate curves or concave areas. Bedrock is sometimes cut into steps, platforms, channels, or ritual forms. It is tempting to look at these shapes and imagine powered grinding tools, because that is how we might approach similar work now. But again, geometry does not identify the tool. A surface produced slowly through pounding and abrasion can look surprisingly regular when only the final stage remains visible. There is also an important distinction between accurate fit and accurate measurement. When two irregular stones meet tightly, it does not necessarily mean both were independently manufactured, according to measurements accurate to a fraction of a millimetre. One stone can be fitted directly against the other. High points can be marked and removed. The stones can be checked repeatedly until the visible joint closes sufficiently. This is essentially a matching process rather than a mass production process. A modern machinist might create two components from drawings and expect them to fit when brought together for the first time. An Inca mason could let one component define the shape of the other. The final result may look equally impressive, even though the path to it is completely different. The distinction becomes especially important at Machu Picchu because builders often incorporated natural rock directly into architecture. Instead of insisting that every foundation begin with a perfectly horizontal artificial platform, they shaped construction around existing outcrops. Walls rise from bedrock. Sacred stones preserve parts of natural formations while other areas are deliberately carved. In certain buildings, the transition between natural mountain and constructed masonry becomes difficult to notice until you look carefully. This is not the behaviour of builders who needed every component to conform to a standardised machine process. It suggests a craft tradition comfortable adapting each structure to whatever geology was already present. The local fracture systems may have helped here as well. Menegat's geological study argues that intersecting faults and fractures influence both the availability of stone and the form of the landscape, with natural breakage producing blocks along recurring orientations. That does not mean the Inca merely picked up perfect building stones and stacked them without modification. Considerable dressing was still required. It does mean that some apparently sophisticated geometry may begin with intelligent material selection rather than brute force cutting. If the mountain offers a block already fractured along two useful planes, an experienced builder keeps those planes and works the rest. A less experienced builder spends 3 days removing material that did not need to be removed, and then wonders why lunch is late. The curved Temple of the Sun is a useful example of how the most impressive work can still reflect ordinary stoneworking principles taken to a high level. The wall follows a controlled curve and sits partly upon a large natural rock formation. The blocks are relatively regular compared with the enormous polygons at Sacsayhuamán. Yet the curved arrangement requires careful adjustment from course to course. Nothing about the geometry demands that the stones were softened or moulded. Each block can be treated as a short segment within a larger curve, with its inner and outer faces dressed accordingly. The process is demanding, but it does not require the entire wall to have been carved from one solid piece or produced using a giant ancient lathe, which is fortunate because storing a giant ancient lathe at 2,400 metres would have created several additional logistical questions. Claims about stone softening appear at Machu Picchu for much the same reasons they appear elsewhere in Peru. Certain surfaces look rounded. Some stones appear to conform closely to irregular bedrock. Corners can be smooth rather than sharp. Yet a chemically softened stone should provide chemical evidence, not merely visual resemblance. A technique capable of turning large quantities of granite into something temporarily mouldable would alter the story of our ancient material science dramatically, and such a discovery would be enormously important. That is precisely why the evidence would need to be strong. We would want reproducible mineralogical changes, residues, treatment layers, tools, processing areas, or other archaeological traces connected directly to the stonework. At present, the famous masonry does not provide that evidence. Mechanical sawing faces a similar test. A machine capable of cutting hard stone efficiently should leave diagnostic traces. Repeated parallel striations, consistent kerfs, characteristic edge behaviour, cutting waste, machine components, or specialised abrasives might begin to build a case. Machu Picchu does contain worked stone, unfinished stone, quarry zones and tool evidence, but there is no established archaeological collection of advanced cutting machinery waiting quietly beside the Temple of the Sun. The most economical explanation therefore remains that known manual stoneworking methods, combined with techniques that may not be fully reconstructed, produce the surviving architecture. The phrase may not be fully reconstructed is important because we should not swing too far in the opposite direction. Saying that no advanced machine has been demonstrated does not mean we know exactly how every surface was made. Archaeologists rarely recover complete craft systems. Wooden gauges disappear, rope devices decay. Pigments used for marking contact can wash away. Abrasives may be difficult to identify centuries later. Specialised techniques can vanish when the specialists themselves disappear. It is entirely possible that an Inca mason would watch one of our modern reconstructions, politely allow us to struggle for several hours, and then point out that we were holding the stone the wrong way. What Machu Picchu demonstrates more clearly than almost any other Inca site is that precision was not merely about attractive joints. Precision existed at the scale of the landscape. Water channels needed reliable gradients, terraces needed to drain without collapsing. Foundations had to remain stable. Stairways had to connect levels shaped by difficult bedrock. Building platforms had to fit a narrow ridge. Structures needed to work with the available geology. A wall could be beautifully fitted and still represent only the final visible layer of a much larger engineering system. Wright's long-term engineering studies are particularly revealing here because they emphasise how much preparation lies below the visible architecture. Excavated foundations and terrace construction show deliberate attention to stability and drainage, while the site's water system demonstrates planned control of both supply and runoff. This makes the usual lost machine question feel slightly misplaced. We stare at one smooth block and ask what cutter produced it, while standing on an artificial landscape whose drainage has been functioning for centuries. Machu Picchu also survived because the builders allowed the site to behave like a mountain instead of pretending it was a flat city lot. Water moves through it. Natural rock remains incorporated into it. Terraces break steep slopes into manageable sections. Many walls are slightly inclined rather than perfectly vertical. Openings tend to use trapezoidal forms familiar across Inca architecture. These choices belong to a wider construction tradition, adapted to the Andes rather than to a mysterious technology that appears only in a handful of inexplicable monuments. This becomes relevant when people compare the finest stonework at Machu Picchu with rougher masonry built directly beside it. If the smooth walls required a lost machine, we would have to explain why the machine was apparently used selectively, while labourers 20 metres away continued building in simpler styles. Perhaps one could argue that different building phases explain the contrast, but we already have a simpler reason. Important structures received more work. The Inca were not trying to demonstrate maximum stoneworking difficulty in every kitchen, doorway, retaining wall and storage building. They concentrated prestige where prestige mattered. There is another useful piece of evidence in the unfinished work. Quarry areas and partially worked stones remind us that the process did not begin with perfectly manufactured blocks. Stones pass through stages. A rough natural block could become a partly dressed block, then a more accurately shaped block, then a final architectural element. Tool marks could be reduced or removed during later finishing. A visitor seeing only the completed face encounters the last stage and may assume that the surface was produced instantly by whatever method created the final appearance. The unfinished material shows otherwise. The same principle applies to the site as a whole. Machu Picchu is often treated as one perfect object conceived and built in a single act, but real construction unfolds over time. Plans change, walls are modified, buildings may be unfinished, stones break, drainage is adjusted. Workers solve unexpected geological problems. Different crews produce slightly different results. Once we accept that, the site begins to look less like the product of a vanished machine, and more like a large human project managed by people who are exceptionally experienced with mountains and stone. There is still genuine mystery here, but it lies in details rather than impossibility. Exactly how were certain irregular contact surfaces transferred from one stone to another? How much abrasion followed hammerstone dressing? What kinds of temporary lifting and positioning systems were used inside confined building areas? How were the finest corners protected during placement? Did different specialist groups have their own techniques? How much practical geological knowledge was formally taught, and how much was learned simply by working with experienced masons? Those questions remain worth investigating because a civilization can leave behind thousands of buildings and still lose much of the knowledge required to reproduce them efficiently. Machu Picchu therefore gives us a useful warning before we move deeper into the question of tools. The absence of iron saws and powered equipment does not mean the Inca lacked sophisticated technology. Technology can exist in foundations, drainage systems, material selection, surveying, labour organisation, road construction, rope work, stone dressing, and accumulated craft knowledge. A simple tool used inside a highly developed process can produce an advanced result. We tend to notice the tool because it can be placed in a museum. The process is harder to preserve. That leads naturally to the question we have been circling since Sacsayhuamán. We have now seen enormous polygonal walls, long-distance stone transport, difficult quarrying, close-fitting masonry, shaped bedrock, controlled curves, sophisticated foundations, and construction performed in environments where mistakes could become very large and very expensive. Archaeology gives us hammerstones, bronze and copper tools for some tasks, abrasives, ropes, ramps, human labour, and evidence of careful planning. The question is no longer whether those things can work at all. We know they can. The harder question is whether they can account for the speed, consistency, finish, and scale of everything we have seen without requiring some additional technique that has disappeared from the record. To answer that properly, we need to stop looking at finished monuments for a while and look closely at the tools themselves, because a hammerstone sounds almost absurdly simple until you ask what a trained craft tradition can actually make it do. After standing beside the enormous walls of Sacsayhuamán, following abandoned monoliths through the landscape around Ollantaytambo, and looking at the carefully fitted masonry of Machu Picchu, we finally arrive at the question that sits underneath almost every argument about Inca construction. What exactly were the builders holding in their hands? It is easy to admire a finished wall without thinking very much about the tool that created it. Once we do think about it, the contrast can feel almost unreasonable. On one side, we have blocks of limestone, granite, and volcanic rock, shaped into controlled surfaces, complicated corners, tight joints, and monumental architecture. On the other side, archaeology gives us hammerstones, wooden implements, ropes, copper and bronze tools, and techniques involving repeated impact and abrasion. There is no hardened steel chisel sitting beside the Temple of the Sun, no surviving iron saw from Sacsayhuamán, and certainly no convenient Inca power drill waiting in a museum drawer with a note saying, "for difficult corners." The obvious question is whether the tools we actually know about are capable of producing the work we have been looking at. The simplest tool in the discussion is also the one people tend to dismiss most quickly: another stone. The phrase hammerstone sounds almost embarrassingly primitive when placed beside the masonry at Cusco or Ollantaytambo. It creates an image of someone picking up the first rock they find and repeatedly hitting a wall until an empire appears. That is not what the archaeological evidence suggests. Hammerstones were selected tools, and different sizes could serve different stages of the work. Jean-Pierre Protzen's investigations of Inca quarrying documented hard hammerstones associated with working areas and unfinished blocks, while his experiments showed that larger stones could be used for rough reduction and splitting, medium-sized hammers for shaping surfaces, and smaller ones for more controlled dressing near edges. His central conclusion was not merely theoretical. He physically reproduced stoneworking operations with tools comparable to those found archaeologically, and argued that the basic Inca sequence of quarrying, shaping, and fitting could be achieved by these simple means. The important word there is simple, because simple is not the same as ineffective. A hammer is one of the simplest tools used by modern craftspeople, yet nobody assumes that an expert carpenter and someone holding a hammer for the first time will produce identical furniture. The effectiveness of a tool depends on the person using it, the material being worked, the angle of impact, the force applied, the sequence of operations, and the amount of time available. Stoneworking adds another variable. The tool does not necessarily have to be dramatically harder than the material in every circumstance. Toughness, fracture behavior, shape, and the concentration of impact force all matter. Protzen documented hammerstones made from durable materials chosen for their ability to survive repeated blows, and he noted that the harder and tougher stones could effectively work the andesite encountered in Inca quarrying. Think about what happens during repeated percussion. The worker is not trying to slice through the block. Each strike concentrates energy into a small area. Tiny fragments break away. Larger flakes can sometimes be detached where the stone permits it. High points disappear faster than lower ones. The surface gradually retreats. To somebody watching for 30 seconds, the method looks hopelessly slow. To somebody repeating the action for hours, the geometry changes. To a crew of trained workers repeating it for days or weeks, an entire block can be transformed. That slow accumulation is one of the hardest things for us to visualize, because the monuments show us the final afternoon of the process, but hide all the mornings that came before it. Protzen's observations are particularly valuable because he found evidence of different stages of working rather than simply staring at completed walls and guessing backward. Quarry blocks preserve large scars where material was removed. More finished surfaces show finer working. Edges could receive smaller scale attention than broad faces. This progression makes sense mechanically. There would be little reason to spend hours delicately pecking a surface, while 20 centimeters of unwanted stone still remained. Rough shaping comes first, followed by increasingly controlled work as the block approaches its intended form. A modern sculptor does the same thing with very different equipment. You do not begin polishing before you have decided where the statue's head is supposed to be. This explains a great deal, but it does not explain everything automatically. One limitation of hammerstone demonstrations is scale. It is one thing to show that a worker can dress a block. It is another to calculate the total labour necessary for dozens or hundreds of large blocks, transport them, fit them, and complete an imperial project within a reasonable period. Critics of conventional explanations often focus on this point, and it is a fair question when asked carefully. How long did the work take? How many stonemasons were involved? How much material could one worker remove in a day? How often did tools break or require replacement? How many blocks were rejected? These questions are much harder to answer than whether pounding works at all. The Inca state, however, changes the calculation. Monumental construction was not performed by one mason working alone until retirement. The empire had access to organised labour on a large scale, and could direct groups toward quarrying, transport, road preparation, masonry, agriculture, and support activities. many operations could happen simultaneously. While one team roughed out blocks at a quarry, another could prepare transport routes, another could dress stones near the construction area, and others could work on terraces or foundations. What sounds impossible when imagined as one person's task can become manageable when divided among hundreds or thousands of people. This does not make the work fast by modern standards, but ancient states did not necessarily need modern construction schedules. There is also a tendency to calculate the labour as though every visible surface had to be created from a completely shapeless mass. That was rarely the case. Builders could select natural blocks whose existing dimensions were useful. Fracture planes could provide finished or nearly finished surfaces. Rockfalls could supply stones already separated from bedrock. Quarry workers could reject material with unsuitable cracks before investing too much time in it. At Machu Picchu, natural geological fractures probably made local stone easier to separate into usable forms. At Ollantaytambo, quarry workers exploited naturally available blocks and fractures. Material selection therefore reduced the amount of shaping needed before anyone began fine fitting. The smartest way to remove a ton of stone is often to choose a block where that ton does not need to be removed in the first place. Hammerstones also help explain a feature that is sometimes used as evidence against them: the rounded character of certain surfaces. Machine cutting tends to encourage us to expect crisp planes and sharp transitions. Percussion working naturally behaves differently. If a rounded hammer repeatedly strikes a stone face, small irregularities are gradually reduced without automatically creating razor-sharp internal corners. Convex surfaces, softened transitions, shallow depressions, and slightly rounded edges are not surprising results. They are exactly the kinds of shapes a controlled pounding process can produce unless additional effort is devoted to sharpening them. This does not mean every rounded surface in Peru was produced in the same way, but it shows why "it looks melted" is not a diagnostic observation. The next tool in the usual list is bronze, and here another misunderstanding appears. The Inca did not live in a world without metallurgy. Andean metalworking had a long history before the Inca Empire, and the Inca used copper alloys, including tin bronze, for tools, weapons, and other objects. Analysis of metal artifacts collected at Machu Picchu has identified evidence of metallurgical work at the site itself. Researchers John Rutledge and Robert Gordon examined 168 metal artifacts from Bingham's collections and identified material associated with casting and working metal. Their study concluded that tin bronze was produced and that bronze chisels were among the tools in use. That immediately makes the image of an entirely Stone Age workforce misleading. Yet bronze introduces its own limitations. A bronze chisel is not an iron or hardened steel chisel. Its edge behaves differently, especially when repeatedly driven against hard rock. A metal tool can deform, blunt, or require frequent maintenance. This means that finding bronze chisels does not prove that the Inca carved every enormous granite face by attacking it directly with bronze. In fact, for much heavy stone removal, a hard hammerstone can make more practical sense. Metal was valuable. Stone suitable for hammering could be obtained far more cheaply. Bronze tools may have been especially useful for particular finishing operations, detailed work, softer materials, or situations where a concentrated edge offered an advantage. The modern assumption that metal must always be superior to stone is therefore another trap. Materials have jobs. A steel dinner knife is made from a technologically advanced material, but you would still rather break concrete with a stone hammer than with your cutlery. Inca craftspeople would not have been concerned with whether a tool looked technologically impressive. They would use whatever worked efficiently for the operation in front of them. A hammerstone could be better for pounding a large area. A bronze chisel might be better for concentrating force into a groove or controlled detail. Abrasion could be better for refining a surface once heavy removal was finished. The toolkit becomes much more plausible when we stop expecting one tool to perform every stage. Abrasion is especially important because it allows a softer implement to work a harder material indirectly. The cutting action does not have to come from the tool itself. Loose grains of hard mineral can become the active cutting material. Sand-containing quartz, crushed stone, or other abrasive particles can grind a surface when rubbed repeatedly against it with water or another carrier. This principle has been used by stoneworkers in many ancient societies. The handle, slab, cord, or tool moving the abrasive can be softer than the stone being worked, because the hard particles trapped between the two surfaces are doing much of the microscopic cutting. This is one reason arguments based only on the absence of iron can be misleading. The reasoning often runs like this: granite is hard, bronze is softer, therefore bronze could not work granite, therefore an unknown technology must have existed, but the conclusion skips percussion and abrasive processes entirely. Hard stone can work hard stone. Loose abrasive can grind hard stone. Natural fractures can reduce the need for cutting. Progress can be slow without being impossible. None of this proves that a particular disputed groove was produced by a particular abrasive method, but it demonstrates that the material problem is not as simple as comparing two numbers on a hardness scale. Abrasion also offers a plausible route from a pounded surface to a smoother one. A worker could first remove the bulk of unwanted material through percussion, leaving a relatively controlled but textured face. Grinding could then reduce the highest irregularities. Finer abrasive could improve the finish further. The entire process works from coarse to fine, much as modern sanding moves through different grades rather than attempting to create a polished tabletop directly from a tree trunk. The final smoothness can hide the violence of the first stage completely. The amount of time required remains the uncomfortable part. Abrasion is not magic. If anyone has ever tried to sand a small piece of hardwood by hand and become bored after 7 minutes, grinding a stone wall may sound like an excellent reason to invent electricity. Yet boredom is not an engineering limitation. The Inca built monumental structures because those structures mattered enough to justify labour that would seem irrational for ordinary construction. We should not estimate ancient feasibility by asking whether a modern homeowner would voluntarily spend 3 months polishing a doorway. There is another possibility that does not require a lost machine but probably mattered greatly: specialization. A person who spends years working, stone develops a practical understanding that is almost impossible to capture in a list of tools. They learn how a particular rock sounds before it fractures. They recognize flaws from colour and texture. They know whether a strike is removing useful material or beginning a crack that will ruin the corner. They learn where to support a block, how to rotate it, which surface should be worked first, and when enough material has been removed. The archaeological record can preserve the hammerstone but not the judgment guiding it. That may be the largest missing tool in the entire discussion. Imagine recovering a modern violin 500 years after the last musician has disappeared. You could identify the wood, measure the strings, reconstruct the bow, and demonstrate that drawing the bow across the strings makes sound. All of that would be correct. It would not mean you had recovered violin playing. The instrument is only part of the technology. Technique exists inside bodies, habits, training, and communities. Traditional masonry is no different. The fitting process provides perhaps the clearest example. A common objection asks how workers without modern measuring instruments could create irregular stones whose joints match so closely. The assumption is that they must have measured complicated surfaces with extraordinary numerical precision, but direct fitting reduces the measurement problem considerably. According to Protson's reconstruction, masons could place or compare stones, identify areas of contact, remove high points from stones already in the wall, and repeat the process until the desired fit was reached. The neighbouring stone becomes the measuring instrument. There are several ways such contact could theoretically be identified. Pigment, clay, dust, damp surfaces, visual inspection, rocking, scratch marks, or simple observation of pressure points could help a skilled worker determine where material needed to be removed. We should be careful here because the surviving evidence does not establish one universal marking recipe for every Inca wall. The broader mechanical principle, however, is straightforward. You do not need to know the mathematical coordinates of a surface if you can compare the two surfaces directly. A carpenter fitting a piece of wood into an irregular opening can do much the same thing. Place it, see where it catches, trim the high area, and try again. Nobody watching the completed fit concludes that the carpenter must have possessed a laser scanner. The difference in Peru is the scale. When the piece of wood becomes a 20-ton stone, every trial fit becomes more difficult. That takes us back to positioning technology, because accurate fitting and heavy transport cannot really be separated. Levers, ropes, inclined surfaces, temporary supports, cribbing, and coordinated labour could allow large blocks to be moved incrementally. A stone does not have to be lifted completely into the air every time someone checks a surface. One edge can be raised enough to insert supports. The block can be tilted. Material can be removed from accessible areas. Small movements can be produced through leverage. The exact procedures used for the largest and most complicated stones remain incompletely reconstructed, but there is a huge mechanical difference between lifting a 100-ton block freely and shifting one side by a few centimetres. The stone can stay mostly where gravity wants it, while the builders negotiate with the rest. This is also why we should resist mental images based entirely on modern cranes. A crane encourages vertical lifting because a crane is good at vertical lifting. Without a crane, builders can design procedures around sliding, tilting, levering, lowering, ramping, and incremental placement. The solution follows the available technology. An ancient method can therefore look strangely indirect to us while being perfectly sensible within its own system. Then comes drilling, another feature frequently cited in lost machine arguments. Holes in hard stone often produce immediate comparisons with rotary drills, because modern holes are usually made by spinning something sharp, but rotation itself is not advanced technology. A hand-operated drill, bow drill or tubular tool working with abrasive material can create circular holes even when the tube is softer than the stone. Once again, abrasive particles can perform the cutting. The existence of a circular hole therefore does not establish a high-speed powered drill. To identify the technology, we would need to study the hole's diameter, taper, wall marks, core, striations, material and archaeological context, rather than simply noticing that it is round. The same caution applies to grooves. A straight groove might be cut by a modern saw, but it can also emerge from repeated rubbing along a guided line. A channel can be hammered first and abraded afterward. Two drilled holes can be connected by removing material between them. There are many ways of arriving at similar geometry. Lost machine theories are strongest only when a feature cannot be reproduced plausibly, with simpler methods, and when the feature contains marks uniquely diagnostic of the proposed machinery. That second requirement is usually where the evidence becomes thin. If the Inca possessed high-speed stone saws, we would expect more than flat surfaces. We would look for repeated kerfs, discarded blades or cutting elements, workshops, distinctive waste, unfinished saw cuts, consistent striation patterns, and some plausible mechanism for powering the equipment. If they used large mechanical grinders, we would expect characteristic wear and tool remains. If they used sophisticated rotary drills, we would look for drill components, repeated standardized diameters, cores, and manufacturing traces. Archaeology has recovered extensive evidence of Inca life and production, including ordinary objects, metalwork, tools, construction debris, quarries, and unfinished architecture. A powerful mechanical stone industry that left only finished stones would be an unusual archaeological pattern. This does not mean every missing tool should have survived. Wood rots, rope decays, metal is recycled. Portable tools can be removed from abandoned sites. Organic materials are especially easy to lose in the archaeological record. It is entirely reasonable to think that Inca builders used wooden frames, gauges, handles, sledges, lever systems, and other devices that are now poorly represented or absent. The important point is scale. The more elaborate the proposed technology becomes, the more supporting infrastructure it should require. A wooden contour gauge disappearing is ordinary. an entire industrial stone-cutting system disappearing without leaving a recognizable production chain is a much larger claim. There is another source of confusion in the word precision. We often use it as though it describes one measurable thing, but stonework can be precise in different ways. A visible joint can be narrow, while the hidden surfaces behind it are less closely matched. A doorway can be geometrically regular without being mathematically perfect. Two surfaces can match one another accurately while neither is perfectly flat. A wall can be extremely well constructed without meeting modern machining tolerances. This matters because some popular claims assign astonishing numerical precision to Inca stonework without showing how the measurements were obtained. Statements that entire walls are accurate to fractions of a millimetre sound scientific because they contain numbers, but a number without a measurement method is decoration. To establish tolerances properly, researchers would need high-resolution surveys of multiple surfaces, clear definitions of what is being measured, and enough data to distinguish original workmanship from weathering, movement, restoration, or damage. The real masonry does not need those exaggerations. A large irregular stone fitted closely enough to remain stable in a dry wall for centuries is already a considerable achievement. Making the claim more dramatic can actually make the builders harder to understand, because it replaces their practical goals with modern manufacturing standards they were never trying to meet. There is also the question of speed, which may be the strongest unresolved part of the conventional reconstruction. We can demonstrate pounding, we can demonstrate grinding, we can demonstrate fitting. What we cannot do easily is recreate an entire major Inca site using only historically appropriate methods with a documented workforce and watch the full sequence from quarry to finished architecture. Such an experiment would require enormous resources and years of work. Without it, estimates of construction time necessarily involve assumptions. That leaves room for techniques we have not identified fully. Perhaps abrasives were used more extensively than surviving evidence allows us to demonstrate. Perhaps metal tools played specialized roles that are underestimated because valuable bronze was recycled. Perhaps wooden devices improved fitting efficiency substantially. Perhaps quarry crews deliberately shaped stones in ways that minimize later adjustment. Perhaps there were methods of checking surfaces that reduced the number of trial placements. None of these possibilities is unreasonable, and discovering one could significantly change our understanding of the labor involved without changing the basic technological world of the Inca. The evidence from Machu Picchu reminds us not to exclude bronze from that world. Metallurgical study of artifacts recovered there found tin bronze production and bronze chisels in use, alongside stone tools involved in metalworking itself. That combination is almost a perfect warning against simplistic labels. Stone tools and bronze tools existed together because technology does not develop by throwing every older tool into a bin when a new material appears. We still use wooden handles, ceramic abrasives, stone aggregate, and steel blades in modern construction. Nobody calls a 21st century building primitive because sand was involved. The answer to our question therefore begins to take shape. Could hammerstones really quarry and dress stone? Yes, experimental work says they can. Could bronze tools have contributed to more detailed operations? Archaeological finds show that bronze chisels existed and were being used. Could abrasion smooth and refine hard rock? Mechanically, absolutely. An abrasive working is a well-established stoneworking principle. Could ropes, levers, ramps, and organised labour position massive blocks? Nothing in mechanics prevents it, and surviving transport evidence strongly supports labour-intensive movement. Does that mean every detail of Inca stoneworking has been explained? No. The largest blocks still raise practical questions about repeated fitting and final positioning. Certain grooves, recesses, drill-like features and surface treatments deserve careful study rather than automatic dismissal. The exact division of labour between pounding, metal tools, grinding and polishing is not preserved as a written recipe. Organic tools are missing. Specialists are gone. Construction traditions were interrupted centuries ago, but the gap between incomplete reconstruction and unknown advanced machinery remains large. Known tools can do far more than their appearance suggests, especially when they are used by specialists with time, organisation, and material knowledge. The mystery is not that a hammerstone is incapable of shaping hard rock. It clearly is capable. The mystery is how the entire toolkit was combined efficiently enough to produce the range of work we find across the Andes, and that is where the investigation becomes more uncomfortable, because once we accept that simple methods can explain a great deal, we can focus much more sharply on the details that seem least comfortable within those methods. The grooves that look unusually regular, the holes that invite comparisons with drills, surfaces that appear ground rather than merely pounded, and stones whose shapes seem difficult to check repeatedly invite a different question. Perhaps the missing element was not an impossibly advanced civilization, but some intermediate form of mechanical assistance that left very little behind. To examine that possibility fairly, we need to look directly at the proposed lost machines themselves and ask what kinds of cutting, grinding, drilling, or even stone softening methods would actually be required to produce the evidence that survives. Once the known toolkit begins to look more capable than it first appeared, the next question becomes much sharper. If hammerstones, bronze tools, abrasives, ropes, levers, and patient fitting can explain a large part of Inca stoneworking, is there anything left that actually requires a lost machine? This is where the discussion becomes difficult, because the phrase lost technology can mean almost anything. It might mean a simple wooden device that has rotted away, a specialised abrasive mixture that no one recorded, a measuring technique passed from mason to mason, or a genuinely unknown mechanical system involving cutting, drilling, or grinding. Those possibilities are not equally likely, and they would not leave the same evidence behind. So rather than asking whether the stones look advanced, it is more useful to ask what a particular machine would have done to them, and whether those traces are actually present. Mechanical cutting is usually the first possibility raised. Some stones at Ollantaytambo and other Andean sites contain narrow grooves, straight-looking channels, recessed lines, and surfaces that can appear surprisingly regular. Seen in a carefully framed photograph, a groove may look as though a blade passed through the stone. The comparison is understandable because modern stoneworking relies heavily on saws, grinding wheels, diamond tools, and rotary cutters. If we encountered the same geometry in a modern workshop, that is probably how it would have been produced. The mistake comes when we move from resemblance to identification. A groove shaped like a saw cut is not necessarily a saw cut. The tool has to be inferred from the microscopic and geometric evidence left by the process, not from the fact that the finished shape reminds us of something in a hardware catalogue. A powered saw cutting hard rock generally leaves a characteristic working pattern. Depending on the blade, cutting medium, speed, and material, we might expect repeated striations, relatively consistent directionality, a curve whose shape reflects the cutting element, or marks showing the movement of the blade through the stone. An unfinished cut is especially useful because it preserves stages that later polishing might erase. If an advanced cutting technology had been used routinely across major Inca building projects, we would also expect the technology to appear repeatedly. There should be many comparable cuts, recognizable toolware, discarded cutting elements, manufacturing areas, or some other evidence connecting the grooves to a consistent mechanical process. The Inca evidence does not currently provide that kind of technological chain. Archaeological study of quarry sites and cut stone walls instead reveals abundant evidence for percussion working. Jean-Pierre Protzen's investigations found quarrying and dressing patterns consistent with the use of hammerstones, and his experiments showed that repeated pounding could produce the required forms and surprisingly controlled surfaces. His reconstruction of Inca stone fitting relied primarily on stone tools, direct fitting, and incremental correction rather than mechanical sawing. This does not prove that no Inca builder ever used a sawing motion with abrasive material, nor does it explain every groove automatically. It does mean that a loss-powered saw is not required by the strongest archaeological evidence we currently have. There is a useful distinction here between a saw and a cutting system. A blade does not necessarily have to be harder than the stone if loose abrasive particles are doing the cutting. Ancient craftspeople in other parts of the world are known to have drilled and worked hard stone using relatively soft tools combined with abrasive material. Experimental research on Bronze Age stone drilling in Crete, for example, has reproduced archaeological wear traces using tubular drills in which abrasive paste performed much of the actual cutting. That is not evidence that the Inca used the same equipment. The culture's periods and archaeological contexts are different. It simply demonstrates the mechanical principle. Hard rock can be cut or drilled without a hardened steel edge if harder grains are trapped between the tool and the stone. This opens a much more realistic area for lost techniques. The Inca may have used abrasive processes more extensively or in more specialized ways than surviving evidence allows us to reconstruct. Sand, crushed minerals, water, wooden guides, cords, or metal tools could potentially be combined in several arrangements. Most of those materials would leave a much weaker archaeological signature than a steel machine. A wooden frame disappears, a fibre cord rots, sand returns to being sand, a bronze component can be recycled, the resulting groove survives far longer than the equipment that made it. That possibility is very different from claiming that the builders possessed motor-driven saws. A hand-operated abrasive cutting device is entirely compatible with the technological world we already know existed in the Andes. It would not require a vanished industrial civilization. In fact, it would be surprising if inventive stonemasons working for generations never experimented with combinations of friction, abrasive material, and guided movement. The problem is demonstrating a particular method rather than merely imagining one that could work. Grinding raises a similar issue. Certain Inca surfaces appear smoother than people expect from hammerstone percussion. Some have broad, shallow depressions, carefully softened corners, or faces that seem almost polished. The common argument is that pounding would leave a rough surface, therefore the builders must have used powered grinders. But the argument skips the finishing stages. Hammerstone working does not have to be the last operation. A surface can be roughed out through impact and then refined by rubbing harder or abrasive material across it. Repeated grinding preferentially removes high points. Finer abrasive improves the finish. Given enough time, the original percussion texture can be reduced dramatically or disappear. Even today, many manufacturing processes use several tools in sequence, because no single operation produces both rapid removal and a fine finish. Rough machining comes first, finishing afterward. An Inca mason could follow exactly the same logic without anything resembling a modern machine shop. Large hammerstones remove a lot of material, smaller ones improve control, grinding refines the surface. Local polishing is used where appearance matters. The technology lies in the sequence. This makes the search for a mysterious grinder harder than it appears. A finished smooth face does not preserve the complete history of the surface. The final abrasive stage may erase earlier marks. Weathering then modifies the result again for several centuries. Damage, restoration, mineral deposits, biological growth, and tourist contact can alter surfaces further. By the time a modern observer arrives with a camera, the stone has gone through a long history that has nothing to do with its original manufacture. Drilling sounds more convincing because a circular hole seems more diagnostic. A hole looks as though something must have rotated, and in many cases that is probably true. Rotation, however, is not itself evidence of advanced machinery. Hand drills are ancient and mechanically simple. A bow drill converts back and forth movement into rotation. A tube can rotate while abrasive grains remove stone at the bottom. A solid tool can peck and grind its way downward. Even repeated manual twisting can produce circular depressions when enough time is available. To decide whether a particular hole was made using a sophisticated rotary drill, archaeologists would need much more information than its shape. Does the wall of the hole contain spiral striations? Is the diameter constant? Does the hole taper? Is there a surviving core? What does the bottom look like? Are there repeated holes with identical dimensions? Is the stone fractured or ground? Are there traces of abrasive? Are related tools found nearby? Without those details, the statement "this looks drilled" tells us very little about the speed or complexity of the drilling apparatus. The bronze evidence from Machu Picchu also warns against assuming that all difficult rockworking had to be performed without metal. Laboratory study of bronze artifacts from Machu Picchu and nearby areas found useware consistent with impacts and sliding contact against hard, brittle material. Several tools had blunt edges and appear to have been used for operations involving rock, while a long bronze bar carried markings interpreted as consistent with stoneworking. Bronze was therefore part of the working environment, even though it was not equivalent to modern hardened steel. A metal tool combined with percussion or abrasive material can accomplish things that neither component would do particularly well by itself. This is why the most plausible missing machinery, if we want to use that word, would probably be mechanically modest. Wooden frames could guide tools, ropes could transmit force, weighted devices might apply steady pressure, simple rotary systems could assist drilling, sledges and lever arrangements could position stones, abrasive cutting could be organised using tools that were mostly organic and therefore unlikely to survive. None of these possibilities would transform the Inca into an industrial society. They would simply make an already sophisticated construction tradition more efficient. The problem comes when the proposed machine becomes much more powerful. Suppose we imagine a motorized saw capable of slicing hard volcanic rock quickly. Now we need an energy source. We need bearings or an equivalent way to control moving parts. We need cutting components capable of surviving repeated use. We need workshops to manufacture and repair them. We need operators. We need waste from production. We need some reason the technology is absent from every other part of Inca material culture. A machine does not exist alone. It belongs to a technological ecosystem. The more advanced the machine, the larger that ecosystem should become. That is one reason the strongest versions of the lost machine theory face difficulty. They sometimes treat the stone wall as though it were the only archaeological evidence that matters. But an advanced machine powerful enough to transform the economics of stone construction should probably affect more than masonry. Similar mechanical principles would be useful in mining, woodworking, metalworking, transport, warfare, and manufacturing. We might expect representations of the device, specialized parts, standardized components, or traditions describing extraordinary mechanical equipment. None of that has been established for the Inca stoneworking sites. There is still a more unusual possibility, and it avoids machinery almost completely. Perhaps the builders did not need to cut the stone in the way we imagine because they could alter the stone itself. This is the origin of the stone softening idea, one of the most persistent alternative explanations for Andean masonry. The theory exists in several forms. In the mildest version, acidic plant extracts or mineral mixtures weakened a thin surface layer, making pounding or abrasion easier. In stronger versions, stone could supposedly be softened deeply enough to become moldable. The most dramatic claims describe blocks being reduced to a paste, pressed into position, or cast into forms before hardening again. The attraction is obvious. Stone softening appears to solve several problems at once. Tight joints become easy, because one block can conform to another. Rounded corners no longer require prolonged grinding. Concave surfaces can be moulded. Tool marks disappear because there is little hard cutting. Massive labour requirements shrink. Suddenly the strange-looking masonry becomes almost straightforward. Unfortunately, solving many problems at once is not evidence that the solution was actually used. Modern discussions of chemically manufactured or softened Andean stone often refer to work by Joseph Davidovits and collaborators. Davidovits has argued that some stone objects and monuments in pre-Inca South America were made using geopolymer-like processes in which mineral material was chemically reconstituted rather than simply carved. His early claims included the possible use of plant extracts, and later research by his group has focused particularly on Tiwanaku and Pumapunku in Bolivia. A 2019 paper in Ceramics International argued, based on microscopic and chemical observations, that certain Pumapunku andesite elements contained unusual organic material consistent with an artificial organo-mineral stone. Davidovits has continued to publish and promote the interpretation that some Andean monuments involved artificial geopolymer stone. Those claims are worth knowing about because stone softening is not merely an invention of modern YouTube videos. Researchers have attempted to create chemical models and test materials, but several important limits have to be kept in view. The best-known Davidovits work concerns Tiwanaku and Pumapunku, not the Inca walls at Sacsayhuamán, Ollantaytambo, or Machu Picchu. Tiwanaku predates the Inca Empire by centuries and belongs to a different archaeological context. Evidence proposed for an artificial stone at Pumapunku cannot simply be transferred several hundred kilometers away and declared proof that Inca polygonal walls were moulded. The second problem is geological continuity. At Ollantaytambo we have identified quarry areas and abandoned blocks associated with transport. We can see large stones at different stages between source and monument. That pattern is exactly what we expect if natural blocks were extracted and moved. A theory in which the final stones were cast from reconstituted material would need to explain why enormous natural blocks were being quarried and transported along the same construction landscape. It would also need to demonstrate that the stones in the walls have a manufactured microstructure, rather than the normal structure of the source rock. A weaker surface softening method would fit the evidence more easily. Perhaps a chemical was used only to assist final shaping rather than creating the entire block. That possibility is harder to rule out because a thin altered layer could weather away or be difficult to detect, yet it still needs physical confirmation. One would want controlled samples from worked and unworked surfaces, petrographic comparison, chemical analysis, and evidence that any alteration is ancient rather than the result of weathering. Without that, a rounded surface remains a rounded surface. There is also a chemical problem hidden in the casual phrase soften granite. Granite and related igneous rocks are not single substances. They are aggregates of several minerals, often including quartz, feldspars and mica, or other components, each with different chemical behaviour. A liquid capable of rapidly turning the whole rock into something resembling clay would need to attack those minerals in a controlled way, without simply destroying the structural integrity of the block. Then, according to the stronger version of the theory, the rock would somehow have to return to a mechanically strong stone afterward. That is a far more demanding process than dissolving a small amount of mineral from a surface. Weathering proves that chemical alteration of rock is possible. Acids can attack certain minerals. Water can transform feldspars over long periods. Hydrothermal systems alter rock naturally. Human beings can accelerate some of these reactions. None of that is controversial. The question is whether the Inca possessed a practical chemical process fast enough, controllable enough, and reversible enough to be useful in monumental masonry. That has not been demonstrated for their major sites. The plant legends make the subject more interesting but not more certain. Stories collected in the modern period describe plants or secret substances capable of softening stone, and such traditions have become a major part of alternative history discussions. The Geopolymer Institute has cited plant extract traditions in support of experimental ideas about chemical dissolution and artificial stone. Oral traditions can preserve remarkable memories, but they also change, combine, and acquire new interpretations over time. A legend can suggest a hypothesis. It cannot replace physical evidence from the wall. There is another possibility that may explain why the story survived even if no literal stone-softening chemical existed. Skilled workers can make hard material appear soft. A mason repeatedly removing tiny amounts from rock may produce curves and joints that later observers find difficult to reconcile with the hardness of the original material. Describing such work as softening stone could become a natural metaphor. Modern people do something similar when we say a sculptor makes marble look like fabric. Nobody thinks the marble was actually woven. The casting version of the idea creates additional problems at sites such as Sacsayhuamán. The enormous polygonal stones contain natural variations, fractures, inclusions, and geological features that would have to remain coherent through any proposed reconstitution process. Casting large artificial stones would require enormous quantities of prepared material, mixing areas, moulds or formwork, and a way to control shrinkage and cracking during hardening. It might reduce quarrying difficulty while creating an entirely new industrial operation. Such an operation should leave evidence somewhere. It is also worth noticing that moulding does not solve transport automatically. If the blocks were cast directly in the wall, raw material still had to be moved. If they were cast elsewhere, the finished stone still had to be transported. If stone was softened only after arriving at the construction site, the original block still needed to be quarried and hauled. A theory can sometimes appear to eliminate one problem only because it quietly moves the same problem to another location. This is why Ollantaytambo remains so important. The abandoned blocks make the transport effort visible. Some stones never reach their destination. If stone could simply be poured into forms beside the temple, hauling giant natural blocks across the valley would be a very strange use of labour. The evidence instead suggests that the blocks themselves mattered as blocks. Cutting, grinding and drilling theories fare better when they remain modest. A specialised abrasive saw is plausible in principle. A hand-powered drilling device is plausible. Wooden templates are plausible. Guided grinding systems are plausible. There could easily have been tools and jigs that archaeology has not preserved. The mistake is jumping from possible to say proven. We need marks that distinguish the hypothetical tool from pounding, abrasion, natural fractures, later erosion, or modern damage. Some famous examples may not even be tool marks at all. Natural mineral veins can weather differently from the surrounding stone and leave straight or groove-like recesses. Cracks can widen through water and temperature changes. Restoration work can introduce modern marks. Quarrying can create regular-looking features through repeated manual action. Context matters more than appearance. A useful investigation would therefore begin with three-dimensional scans and microscopic examination rather than photographs. Surface textures could be mapped at high resolution. Striation directions could be measured. Geological features could be separated from working traces. Experimental samples produced by hammerstone pounding, metal chiseling, abrasive sawing, grinding, drilling, and chemical treatment could then be compared blindly with archaeological surfaces. That kind of work could identify methods far more convincingly than an argument based on what a groove resembles from 2 meters away. The same approach could test stone softening claims. Samples from suspected work surfaces could be compared with fresh interior material from the same geological source. Researchers could examine mineral boundaries, chemical alteration, amorphous layers, residues, recrystallization, and microscopic deformation. If a chemical process were genuinely involved, it should eventually become possible to describe what changed in the rock, and how consistently that change appears across worked surfaces. This would be an extraordinary discovery, and archaeology would have no reason to hide it. A demonstrated ancient chemical stoneworking technique would expand our understanding of Andean science dramatically. The idea that mainstream researchers would refuse such evidence simply because it makes the Inca more sophisticated misunderstands how discoveries work. The person who could demonstrate a reproducible lost Inca stone treatment with secure archaeological evidence would have a very interesting career. Until then, the balance of evidence remains less spectacular. Percussion working is directly supported. Bronze tools show wear consistent with stone contact. Abrasive methods are mechanically capable of producing drilling and grinding effects, even with relatively soft tool materials, as experimental archaeology in other ancient contexts demonstrates. Quarry sites, unfinished blocks, and transport landscapes connect natural stone sources to the monuments. The advanced mechanical and chemical alternatives remain possibilities of very different strengths, but none has yet replaced the simpler reconstruction. What may genuinely be lost is the equipment between the hand tool and the finished wall. A small wooden support frame does not sound exciting enough for television, but it might transform how efficiently a heavy stone could be checked. A contour transfer device could reduce days of fitting. A particular abrasive mixture might double grinding speed. A clever rope arrangement could let workers rotate a block without lifting it fully. A metal punch shaped for a specific groove might explain features that look mysterious when we assume only round hammerstones were available. These are the kinds of technologies most likely to vanish because almost everything involved could decay, wear out, or be recycled. There is also a larger lesson here about technological progress. We often imagine history as a straight ladder in which every later society possesses everything earlier societies knew, plus something new. Real technological history does not work that way. Techniques disappear when economies change. Specialized crafts vanish when patrons disappear. Materials become unavailable. Political systems collapse. A method that makes sense when thousands of workers are organized by an imperial state may become useless when construction shifts to smaller local projects. A craft can be forgotten not because it was impossibly advanced, but because nobody needs to practice it anymore. That possibility becomes especially important when we turn to the claim that the most sophisticated stonework may not have been Inca in the first place. Even if no powered saw or stone softening formula existed, the Inca did not emerge into an empty Andes. They inherited roads, agricultural systems, religious ideas, settlements, and building traditions from societies with long histories before the imperial expansion from Cusco. The question is whether they also inherited some of the megalithic foundations themselves, and whether the differences visible in stonework at certain sites preserve distinct building phases that reach back before the empire. To examine that properly, we have to stop asking only what tools could shape the stones and begin asking who was shaping them, when, and what was already standing when the Inca arrived. Once we stop treating every unusual groove or smooth surface as evidence of a machine, another possibility becomes much harder to ignore. Perhaps the people who built the great imperial monuments of the Andes did not invent every part of their stoneworking tradition themselves. The Inca Empire was enormously powerful, but it was also remarkably young. Its great territorial expansion took place mainly during the 15th century, only a relatively short time before the Spanish arrived. The Andes, meanwhile, had already been home to cities, states, ceremonial centres, road systems, terraced agriculture, metalworking traditions, and monumental stone architecture for many centuries. The Inca did not step into an empty landscape and suddenly discover how to organise mountain societies. They inherited a world already filled with knowledge. The real question is how much of their famous masonry belonged to that inheritance, and whether some of the structures we routinely call Inca were actually older buildings that the empire adopted, repaired, expanded, or rebuilt. This idea needs to be handled carefully because there are two very different versions of it. The first is supported by a great deal of archaeology. The Inca developed within a long Andean cultural sequence and borrowed, adapted, continued, and transformed earlier traditions. The second is much stronger. The finest polygonal and megalithic walls at places such as Sacsayhuamán, Ollantaytambo, and Machu Picchu were supposedly built by an unknown civilization long before the Inca, who later found the ruins and simply built inferior structures on top. Those two statements are often treated as though they mean the same thing. They do not. A civilization can inherit architectural traditions without inheriting completed buildings, just as modern architects can inherit Roman ideas without secretly discovering an intact Roman airport beneath the city. Cusco itself makes the long history impossible to ignore. UNESCO describes the imperial city as the result of a 15th century redesign under Pachacuti, following more than 3,000 years of pre-Inca occupation. It describes Cusco as the product of a long sequence of indigenous development rather than a city that suddenly appeared with the mature empire. By the time Pachacuti and his successors transformed Cusco into the political and religious centre of Tawantinsuyu, generations of people had already been living, building, farming, organising settlements, and creating sacred landscapes throughout the valley. That alone makes it reasonable to expect older structures beneath later ones. Sacsayhuamán provides one of the clearest examples. Archaeological work in the Cusco region has found substantial deposits of pottery, associated with what archaeologists call the Quilque tradition, dating to the late intermediate period before the mature imperial Inca phase. Brian Bauer and R. Allen Covey noted that deep deposits of Quilque ceramics occur at Sacsayhuamán as well as across major sectors of Cusco, demonstrating significant occupation of the area before the imperial period. This means that people were using the hill long before the famous 15th century monumental expansion, normally associated with the Inca rulers. That fact is sometimes presented online as though archaeology has accidentally admitted that an unknown civilization built the giant zigzag walls. The evidence does not say that. Pre-Inca occupation of a site and pre-Inca construction of every surviving structure at that site are separate questions. People can occupy a hill for centuries before somebody builds an enormous wall on it. London existed before the Houses of Parliament, but that does not make the Houses of Parliament Roman. The Quilque evidence is interesting for another reason. Older archaeological literature sometimes treated Quilque as a separate culture preceding the Inca, while more recent interpretations often emphasize continuity between those populations and the communities from which the early Inca state developed. Bauer and Covey used the distribution of Quilque material to reconstruct processes of state formation around Cusco, rather than describing a clean replacement in which one mysterious population vanished and an unrelated Inca population suddenly appeared. This makes the simple question, was it Quilque or Inca, less useful than it sounds. Political identities can change while populations, skills, settlements, and craft traditions continue. Imagine a town where masons have worked stone for 10 generations. During the 11th generation, a new political dynasty takes control, reorganises the labour force, expands the territory, and begins commissioning far larger projects. Archaeologists 500 years later might give the earlier pottery one name and the imperial pottery another. The masons themselves may have regarded their work as part of a continuous tradition learned from parents and grandparents. Cultural labels are extremely useful for archaeology, but ancient craftspeople did not wake up one morning, check the date, and announce that the old archaeological period was over. This becomes especially important when thinking about the apparent sophistication of mature Inca masonry. A visitor can look at Sacsayhuamán and wonder how an empire that expanded so rapidly acquired such specialised stoneworking abilities. One possible answer is that it did not acquire them suddenly. The skills may have developed through earlier regional traditions before the empire existed, then expanded dramatically when the imperial state became capable of mobilising thousands of workers and concentrating specialist knowledge on royal projects. There were much older examples of sophisticated stone architecture elsewhere in the Andes. Tiwanaku, near Lake Titicaca in present-day Bolivia, flourished centuries before the Inca Empire. UNESCO dates its development as a planned urban ceremonial centre, mainly between roughly AD 400 and 900, and describes precisely carved ashlar masonry, monumental stone buildings, large monoliths, sophisticated drainage, and highly developed techniques for carving and polishing different kinds of stone. Anyone suggesting that advanced stoneworking first appeared in the Andes with the imperial Inca therefore has the chronology backward. Major stoneworking traditions were already old by the time Pachacuti began transforming Cusco. Tiwanaku is particularly interesting because some of its stone architecture looks remarkably controlled. Blocks at the monumental centre were cut into regular forms. Doorways were carved from large pieces of andesite, Recesses, right angles, decorative elements, and carefully finished surfaces appear in structures built centuries before the famous Inca sites reached their final form. Tiwanaku stoneworkers were not building the same kind of architecture found at Sacsayhuamán, but they demonstrate something important. Andean craftspeople had been solving difficult problems in hard stone long before the Inca Empire. The Inca themselves were aware of Tiwanaku's antiquity. Early colonial accounts recorded traditions in which Tiwanaku was regarded as ancient even from the Inca perspective, and archaeologist John Janusek has argued that the Inca connected themselves ideologically with the older centre, treating it as a place of ancestral significance and emulating aspects of its monumental tradition. This does not prove that Tiwanaku masons travelled through time to construct Sacsayhuamán. It does show that the Inca were perfectly capable of encountering impressive older ruins, recognising their authority and incorporating them into their own understanding of history. That is important, because empires do this constantly. Rome absorbed Greek art and architecture. Medieval rulers built churches around earlier sacred locations. Spanish colonists placed churches over indigenous temples. The Inca themselves incorporated regional sacred places as their empire expanded. Powerful states rarely erase every older tradition and begin again. More often, they take possession of important landscapes, reinterpret them, improve them, and claim them. Wari provides another possible source of continuity. The Wari state flourished in parts of Peru during the Middle Horizon, centuries before the rise of Imperial Cusco, and established an important centre at Piquilacta not far from the Cusco Valley. Regional archaeological research shows that Wari influence in the Cusco region was real, but uneven rather than complete. A large survey published in the Journal of Anthropological Archaeology found evidence for Wari colonisation and interaction, while concluding that its power across the Cusco region was limited and discontinuous. This is more useful than imagining a single predecessor civilization handing the Inca a complete engineering manual. The archaeological picture is one of overlapping regional traditions, migrations, political changes and cultural borrowing. The period after Wari and Tiwanaku declined is especially important. Their political systems collapsed, but human beings did not vanish from the Andes. Communities remained. Techniques remained. Farmers continued farming. Craftspeople continued making things. Political fragmentation can destroy an empire without deleting every practical skill possessed by the people who lived within it. Research on the aftermath of Tiwanaku, for example, shows significant cultural continuity in regions previously connected to the state, even after its political collapse around the beginning of the second millennium. Knowledge can survive without the government that originally organised it. This offers a much more plausible version of the lost civilization idea. Perhaps the Inca inherited skills whose distant origins reached back through several earlier societies. They may have recruited specialist communities with established stoneworking traditions. They may have studied earlier monuments. They may have adapted techniques developed around Lake Titicaca, Cusco, or other highland regions. Over time, the imperial state could have combined those traditions with its own architectural preferences and enormous labour resources. None of that requires an unidentified civilization with machines more advanced than anything else in pre-Columbian America. The stronger argument usually begins with differences in masonry. At many Andean sites, people notice beautifully fitted stones below rougher construction and assume the sequence must represent technological decline. The lower masonry is declared ancient and advanced, while the upper masonry is assigned to the Inca because it looks simpler. This seems intuitive because buildings normally grow upward. If the bottom is older and better, perhaps the better builders came first. Unfortunately, archaeology refuses to be that convenient. Walls are repaired, upper structures collapse and are rebuilt. Different parts of the same building can have different purposes. A foundation may receive larger stones because it carries more load. A ceremonial facade may receive carefully fitted masonry, while an ordinary extension is built quickly. Later colonial construction can sit directly over Inca walls. Modern restorations can add still another layer. Even within a single construction campaign, specialists may produce prestige masonry in one area, while other crews build practical retaining walls nearby. The Inca were particularly fond of architectural hierarchy. Important buildings could receive finely dressed stone, while less prestigious structures used much simpler masonry. This is visible at Machu Picchu, where several construction styles coexist across a site strongly associated with the Inca imperial period. The existence of rough and fine work together therefore weakens the idea that every quality difference represents a chronological boundary. We should also ask what evidence would establish the stronger pre-Inca megalithic hypothesis. Ideally, archaeologists would find secure material beneath or inside the construction that predates the imperial period, together with a clear structural relationship showing that the enormous wall belonged to that earlier context. Quarry evidence might show that the blocks were extracted before the Inca occupation. Earlier settlements could contain unfinished stones made using the same techniques. Tools and workshop debris might link the masonry to an older population. Similar monumental walls could appear at securely dated pre-Inca sites in a developmental sequence leading toward the later style. Some pieces of that larger story do exist, but not in the form required to transfer all of the famous megalithic walls away from the Inca. Earlier Andean societies absolutely built sophisticated stone monuments. Tiwanaku provides one strong example. Pre-imperial occupation at Sacsayhuamán is also real. What is missing is a convincing archaeological chain showing that an unidentified civilization constructed the enormous surviving zigzag terraces and that the Inca merely found them. The historical evidence actually creates a problem for that claim. Spanish-era chroniclers who encountered Inca traditions about Cusco associated the great works at Sacsayhuamán with Inca rulers and labour organisation. Colonial texts are never simple recordings of the past, and they must be treated critically, but dismissing them completely creates an odd situation. We would be rejecting both the archaeological relationship to imperial Cusco and indigenous traditions of construction simply because the stones look too impressive. The argument becomes weaker still when it claims that the Inca themselves admitted they could not build such things. This often comes from mixing accounts of different sites together. Tiwanaku genuinely was regarded as ancient by the Inca and by local people encountered during the colonial period. Janusek discusses early reports in which people near Tiwanaku rejected the idea that the Inca had built those monuments because the site preceded them. But Tiwanaku is not Sacsayhuamán. Evidence that the Inca recognized one ancient pre-Inca center cannot be transferred automatically to every impressive stone structure in Peru. It would be like finding a medieval English account acknowledging that Stonehenge was already ancient and concluding that medieval people therefore built none of England's castles. The more interesting possibility lies between the extremes. Sacsayhuamán could contain earlier occupation and earlier construction, while its giant surviving walls largely belong to later Inca expansion. An imperial architect could reuse an older sacred landscape, while building something radically larger upon it. Older foundations might survive beneath newer structures. Earlier retaining walls could be incorporated, material could be quarried from previous buildings. The result would genuinely be layered without requiring the most dramatic architecture to belong to an unknown civilization. This kind of layered history is common throughout the Andes. Important places remain important. A spring worshipped by one community can become a state shrine under another. A hilltop settlement can become an imperial centre. A road can be widened rather than replaced. The Inca were extraordinarily effective at incorporating existing regional systems into their empire, and their architecture often operated in exactly that political environment. Tiwanaku also tells us why the idea of inheritance should not be dismissed merely because direct technical continuity is difficult to trace. Its builders had sophisticated knowledge of stone carving, drainage, urban planning, and monumental construction centuries before the Inca. UNESCO explicitly notes that technologies and innovations associated with Tiwanaku influenced succeeding civilizations and spread through the Andes. We do not need to imagine an uninterrupted guild of Tiwanaku master masons quietly waiting 400 years for an Inca emperor to call. Knowledge can fragment, move, be reinvented, and survive in altered forms. The Wari example reinforces that point. Their influence around Cusco did not erase local traditions. Archaeological evidence instead suggests complicated interaction between outside state power and existing communities. Later Cusco society emerged from that complicated landscape. When the Inca state eventually became imperial, it had access not only to local skills but also to specialists drawn from conquered territories. The empire moved populations deliberately for economic and political purposes, meaning expertise could circulate across enormous distances. A technique did not have to originate in Cusco to become part of Inca imperial construction. This may help explain why mature Inca architecture sometimes appears so suddenly in the archaeological record. What looks sudden at the level of imperial monuments may represent the concentration of much older regional knowledge, a state capable of bringing together skilled masons, quarry workers, rope makers, engineers, administrators, and huge labour forces could produce results far beyond what any small local community had previously attempted, even if none of the individual techniques were new. The difference is similar to building a cathedral. The invention is not necessarily one miraculous tool. It is the coordination of many existing skills at an unprecedented scale. There is also a practical reason the earlier builder theory remains attractive. It gives us a satisfying explanation for uncertainty. When we cannot reconstruct exactly how a stone was fitted, we can assign the problem to someone else. If the Inca toolkit seems inadequate, an earlier culture receives a better one. If that culture leaves no tools, the tools are described as lost. The explanation becomes difficult to disprove because every missing piece of evidence is treated as proof that something vanished. Archaeology has to work in the opposite direction. The unknown builder should be introduced only when the known evidence requires one. At the moment, the evidence requires an older Andean tradition. It requires significant pre-Inca occupation of Cusco. It requires earlier sophisticated stoneworking at places such as Tiwanaku. It requires Wari and other regional influences. It requires continuity through political collapse. It requires the Inca to have inherited a landscape already filled with sacred places and engineering knowledge. It does not currently require us to remove the major imperial monuments from the Inca and give them to an unidentified civilization. That conclusion still leaves us with something much more interesting than a simple yes or no. The Inca may have been less like inventors working from a blank page and more like the final great organizers of a technological tradition whose roots extended deep into Andean history. Some methods they used may have been centuries old, others may have been borrowed and improved. Some specialists may have carried knowledge originating far outside Cusco. Certain sacred locations may indeed preserve earlier foundations beneath imperial architecture. When the Inca built, they were building inside a world already ancient to them. Seen this way, the question changes. Instead of asking whether the Inca stole mysterious walls from a forgotten civilization, we can ask how many generations of experimentation were hidden inside an Inca wall by the time it was finished. A mason at Sacsayhuamán may have been using techniques whose earliest origins nobody in his own lifetime remembered. He did not need to know who first discovered a particular method any more than a modern carpenter needs to know who invented the saw. There is one final complication. Even if earlier traditions explain where some of the knowledge came from, they do not tell us whether that knowledge was genuinely lost after the Spanish conquest. The imperial construction system collapsed rapidly. Specialist communities were disrupted. Labour obligations changed. Religious institutions were destroyed or transformed. Monumental projects were abandoned. Stones were removed from Inca buildings and reused in colonial ones. Whatever chain of teaching had produced elite masons was no longer operating in the same way. So perhaps there really is forgotten engineering at these sites, but not in the form usually imagined. The lost element may be the accumulated method that linked ancient Andean stone traditions to the mature Inca building system. how quarrymen selected blocks, how masons read fracture patterns, how teams transferred irregular contours, how supervisors coordinated transport, how workers combined pounding with abrasion, and how specialists decided exactly when a stone was ready to be placed. Some of those practices may have come from traditions much older than the empire itself, while others were probably developed under Inca rule. That brings us to the hardest question of the entire investigation. We have seen that known tools can accomplish far more than they first appear capable of doing. We have found no convincing evidence requiring powered stone-cutting machines, or a material capable of turning granite into clay. We have also seen that the Inca inherited an old Andean world where sophisticated stone construction existed centuries before their empire. None of this makes the extraordinary masonry ordinary. It simply moves the mystery away from impossible machines and towards something harder to recover: the practical knowledge of people who knew exactly what they were doing. The stones can tell us that knowledge existed, but deciding how much of it we truly understand requires putting all of the evidence together and asking what explanation leaves the fewest problems behind. After moving through Sacsayhuamán, Ollantaytambo, and Machu Picchu, after looking at hammerstones, bronze tools, abrasives, hypothetical drills, possible grinding systems, stone softening claims, and the much older architectural traditions of the Andes, we can finally return to the question we began with. Did the Inca use machines we no longer understand? The most honest answer is more interesting than either extreme usually offered in discussions of these sites. There is strong evidence that Inca builders could quarry, shape, transport, fit, and finish difficult stone using relatively simple tools, combined with large labour forces and very sophisticated practical knowledge. There is no convincing archaeological evidence that they possessed powered stone-cutting machines, industrial drills, or a process capable of turning granite into mouldable clay. At the same time, it would be equally unreasonable to claim that every detail of their construction system has been reconstructed. Something has been lost. The important question is, what kind of thing was lost? The easiest mistake is to imagine only two possibilities. Either modern archaeology has a complete explanation for every stone, or some unknown advanced technology must have existed. Real history usually gives us a much messier middle ground. Jean-Pierre Protsen's experimental work remains important because it demonstrated that large parts of Inca stoneworking do not require mysterious machinery. By studying ancient quarries, unfinished blocks, working traces and completed masonry, then testing comparable techniques himself, Protsen showed that stones could be selected from rockfalls or detached from rock faces, split using large hammerstones, shaped with smaller hammerstones, and fitted through repeated adjustment. His reconstruction involved working already placed stones so that they received the next block in a trial and error fitting process. That does not tell us every movement made by every mason, but it establishes something fundamental. Apparently extraordinary masonry can emerge from tools that look extremely ordinary. There is an understandable resistance to that conclusion, because the finished walls seem too refined for the tools. Put a carefully fitted polygonal block beside a rounded hammerstone in a museum display and the relationship almost feels insulting. Surely there must be something missing between the two. In one sense, there probably is. What is missing is the worker, the training, the sequence, the temporary equipment, the organisation, and the enormous amount of repetition that happened before the wall became a wall. A hammerstone lying motionless in a glass case tells us almost nothing about the system in which it was used. It is rather like displaying a chef's knife and wondering how such a simple object could possibly produce an elaborate meal. The knife did not produce the meal by itself, and the hammerstone did not produce Sacsayhuamán by itself. Consider the journey of a single large stone. The process begins before the first strike. Someone has to decide which stone is worth using. Natural fractures matter. Existing shape matters. Mineral flaws matter. The direction in which the stone is likely to split matters. A good choice at the quarry can eliminate enormous amounts of later work. Once the block has been selected, rough material must be removed without introducing cracks that make the stone useless. The block must then be moved, perhaps through difficult terrain, while teams control its direction and prevent an expensive piece of imperial architecture from becoming an expensive object at the bottom of a hill. Additional shaping may occur closer to the construction site. Contact surfaces have to be checked. High points have to be removed. The stone may need to be shifted repeatedly by small amounts. Only when the builder is satisfied can it take its final position. None of those steps requires an electric motor. All of them require expertise. That difference is probably at the heart of the mystery. Modern technology often transfers skill from the worker into the machine. A computer-controlled stone cutter can reproduce a shape accurately even when the person operating it could never carve that shape by hand. Traditional craft works in the opposite direction. The tool can be simple because much of the complexity exists in the person using it. When that craft tradition disappears, we are left with the simple tool and the complex result. Naturally, we start looking for another machine because we can no longer see where the sophistication actually lived. Sacsayhuamán demonstrates this particularly well. Its enormous limestone blocks are impressive not simply because they are large, but because they belong to a complete structural system. The three great zigzagging walls are associated by Peru's cultural authorities with the imperial Inca development of the site beginning under Pachacuti and continuing under later rulers. The wider complex included sacred, political, hydraulic and monumental functions, while part of its stone was later removed and reused in colonial Cusco. The walls we see now are therefore surviving portions of a much larger construction program. Their blocks had to be selected, shaped, moved, placed, drained and incorporated into architecture that performed successfully in a difficult seismic environment. The impressive joint is only the visible edge of the engineering. Ollantaytambo gives us perhaps the most useful evidence because the construction process is spread across the landscape, rather than hidden inside finished architecture. Quarries, unfinished blocks, transport routes, and stones abandoned before reaching their destinations allow us to connect natural rock sources with monumental building. This is difficult to reconcile with the strongest versions of the stone casting theory. If builders could simply manufacture giant blocks beside the temple, hauling large natural stones through the valley would be a very peculiar use of labour. The abandoned stones make much more sense if natural blocks themselves were being selected, worked and transported. They also remind us that the process was difficult. Not every stone made it. That is an important observation because advanced machine theories sometimes assume that the apparent perfection of the finished work implies an almost effortless technology. The unfinished evidence tells another story. Construction left failures, interruptions, incomplete surfaces, blocks in transit, and work that was never completed. The Inca building system was powerful, but it was not magical. It struggled with the same basic problems that any builder faces. Material breaks, transport goes wrong, plans change, rulers die, political conditions shift, and occasionally the enormous stone simply remains where everyone finally stopped pulling it. Machu Picchu adds a different kind of evidence. There, the most impressive engineering may not be the finely fitted stone that appears in photographs. Long-term engineering studies have shown how much effort went into foundations, site preparation, drainage, water supply and slope management. The site receives very heavy rainfall, yet Inca builders created systems that controlled both surface water and groundwater while stabilizing terraces and foundations. Studies by Kenneth Wright and colleagues describe substantial drainage infrastructure and carefully planned hydraulic works, including a gravity-fed water system supplying a sequence of fountains. This matters because drainage does not fit neatly into the Lost Machine story. It is sophisticated without being mysterious. There is no single impossible device to point at. Instead, there is a series of sensible decisions applied consistently across an entire settlement. Water moves where it is supposed to move. Foundations are prepared appropriately. Terraces contain material that allows drainage. Channels maintain useful gradients. The landscape itself becomes part of the engineering design. This is what advanced knowledge often looks like in practice. It is not necessarily one miraculous machine. It is hundreds of correct decisions that prevent something from going wrong. The same principle probably applies to the stonework. We may be looking for one missing invention when the real answer was a well-developed system. A quarry specialist knew how to select stone. Another worker understood rough shaping. A transport supervisor knew how to coordinate ropes and labour. Masons understood fitting. Other specialists may have worked on finishing. Administrators supplied food and organised workers. Roads and storehouses supported the operation. The Inca state itself was part of the construction technology because it made large coordinated projects possible. That helps explain why reproducing one stone experimentally does not reproduce Sacsayhuamán. The problem was never just whether a hammerstone can remove material. It was whether a society could organise all of the necessary tasks repeatedly and reliably at monumental scale. The Inca clearly could. The machine question nevertheless remains worth asking because some details are still poorly understood. We should not pretend otherwise. Wooden equipment would rarely survive. Fibre ropes decay. Temporary frames disappear. Metal tools can be recycled. Abrasives may leave little evidence. Marking substances used during fitting may wash away. A contour transfer device made from wood could vanish completely while the stone shaped with its help survives for 5 centuries. Specialised procedures can therefore disappear almost without a trace. This is where the phrase lost technology becomes reasonable, provided we define technology broadly enough. There probably are lost technologies at Inca sites. A forgotten rope arrangement is technology. A wooden lifting frame is technology. A method for transferring an irregular contour is technology. A particular abrasive recipe is technology. A sequence for fitting very heavy blocks without repeatedly lifting them completely is technology. A technique for reading natural fractures before quarrying is technology. We may never recover all of those details. That is very different from saying the Inca possessed a mechanical stone industry comparable to modern powered equipment. An advanced cutting machine should normally leave evidence beyond the object it produced. Cutting elements have to be manufactured. Moving parts wear. Power must come from somewhere. Workshops are needed. Waste is generated. Maintenance produces debris. If the technology were common enough to account for monumental construction across multiple sites, we would expect it to appear as a wider technological system rather than only as an interpretation of smooth stone surfaces. No such system has been established archaeologically. The stone softening theory faces the same basic problem. It is not enough for a block to look slightly moulded. A chemical process capable of substantially altering hard rock should alter the rock physically or chemically in a detectable way. The stronger versions of the hypothesis would require an especially dramatic process because granite, andesite, and similar rocks contain multiple minerals that respond differently to chemical attack. Transforming a massive block into a mouldable substance and then returning it to strong stone would be a remarkable material technology. If evidence for such a process were demonstrated through reproducible geological analysis, it would deserve enormous attention. At the moment, that demonstration does not exist for the major Inca sites we have been discussing. Claims of artificially reconstituted stone have been proposed elsewhere in the Andes, particularly in connection with Tiwanaku and Pumapunku, but those claims remain distinct from evidence at imperial Inca sites. More importantly, Tiwanaku itself shows why we do not need to invent a technologically empty Andes before the Inca. UNESCO describes Tiwanaku as a major pre-Inca centre that flourished many centuries earlier, with accurately carved stone, polished materials, sophisticated drainage, and innovations that influenced succeeding Andean civilizations. Advanced stoneworking already had a long regional history before the Inca Empire reached its height. This gives us a better way to think about inheritance. The Inca probably did inherit technology, but not necessarily finished mysterious walls from an unknown civilization. They inherited generations of Andean experimentation. Earlier builders had already learned how different stones behaved. Earlier states had already organized monumental projects. Roads, agricultural systems, hydraulic engineering, metalworking, stone carving and religious architecture all had histories extending before Imperial Cusco. The Inca could draw upon those traditions, recruit specialists from conquered regions, improve existing methods, and concentrate labour on a scale that smaller societies could not. That makes their achievement more understandable without making it less impressive. There is sometimes a strange assumption in alternative history discussions that giving the Inca ordinary tools somehow diminishes them. The opposite is true. Saying that a wall required a vanished laser is easy. The laser does the difficult work. Saying that thousands of complicated stones were produced using percussion, abrasion, careful fitting, intelligent material selection, and highly organised labour gives the accomplishment back to the people who actually built them. The hammerstone explanation sounds primitive, only because we confuse sophisticated results with sophisticated-looking tools. A violin is made from wood and strings. A paintbrush is hair attached to a handle. A surgeon's scalpel is essentially a sharp piece of metal. Human history is full of simple tools producing extraordinary results because the complexity lies in technique. Inca masonry belongs comfortably within that larger pattern. Still, some caution is necessary on the archaeological side as well. It would be a mistake to take successful experiments with hammerstones and conclude that every disputed surface has therefore been solved. Experimental archaeology establishes possibility, not automatic identity. Protzen showed that simple means could reproduce important features of Inca quarrying and fitting. That gives us a strong baseline explanation. Individual grooves, unusual holes, concave surfaces, bosses, recesses, and finishing patterns can still deserve separate examination. Some may represent techniques we have not identified correctly. Better microscopic surface studies and three-dimensional scanning could help distinguish percussion, abrasion, drilling, natural weathering, and later damage much more reliably than photographs can. The most useful future research would probably be less dramatic than another argument about whether the stones were melted. Researchers could create experimental reference collections using different historically plausible techniques, then compare those surfaces microscopically with archaeological examples. Worked and unworked stone from the same geological sources could be analysed for chemical alteration. High-resolution scans could measure joints through accessible depth, rather than only along their visible edges. Quarry marks could be mapped systematically. Experimental transport projects could record how much labour is actually required to control blocks of different sizes on realistic slopes. These studies would not produce exciting thumbnails involving glowing ancient machines, but they might answer some of the questions those thumbnails are supposed to solve. There is also a larger question about why we find these monuments mysterious in the first place. Part of the answer is simply that the construction process is gone. We are surrounded by modern objects whose manufacturing we do not personally understand, but we know factories exist, so they do not feel mysterious. Most of us could not manufacture a smartphone, an elevator, or even a good stainless steel spoon from raw material. We accept them because the industrial system that produces them is visible somewhere in the world. The Inca industrial system is gone. The quarry remains, but the quarry crew does not. The road remains, but the transport teams do not. The wall remains, but the master mason is gone. The hammerstone remains, but the person who knew exactly how to hold it does not. The empire that organised all of them disappeared centuries ago. When only the finished object survives, ordinary skill can begin to look supernatural. There is another psychological effect at work. Large things make simple methods feel inadequate. Tell someone that a 10-kilogram stone was dragged with rope and nobody is surprised. Tell them a 100-ton stone was dragged with rope and suddenly the rope seems suspicious. Yet the underlying physics does not change simply because the number becomes uncomfortable. More mass requires more force, better preparation, stronger equipment and greater control, but it does not introduce a new law of nature. The challenge becomes organisational and practical. Ancient societies repeatedly solved such problems because monumental building was one of the things governments were willing to spend enormous resources on. Egyptian obelisks, Roman monuments, Medieval cathedrals, Southeast Asian temples, and Andean walls all remind us that human beings can devote astonishing amounts of labour to structures whose practical purpose does not explain their cost. Political authority, religion, identity, competition, and prestige can justify projects that would make a modern accountant begin blinking very rapidly. The Inca also lived in a world where stone carried political meaning. Imperial architecture was not simply shelter. Carefully fitted masonry marked important places and expressed state power. Different construction quality at the same site is therefore not surprising. The extraordinary stonework was often extraordinary precisely because it was meant to be noticed. That helps answer another question we encountered earlier. Why use irregular polygonal blocks when rectangles seem easier? Part of the answer may lie in material and seismic performance. Part may lie in the shapes naturally available. Part may come from established architectural traditions, and part may simply be that the finished walls created a distinctive visual language associated with Inca authority. Engineering decisions can be practical and symbolic at the same time. So what do the stones actually tell us? They tell us that the Inca and their Andean predecessors understood stone extremely well. They tell us that natural geology was used intelligently, rather than treated as an obstacle to be erased. They tell us that quarrying and transport were organised at scales requiring substantial administrative capacity. They tell us that simple tools can become highly effective when used inside mature craft traditions. They tell us that precision was applied selectively rather than uniformly. They tell us that infrastructure such as drainage and foundations mattered as much as attractive masonry. They tell us that earlier Andean civilizations had already developed sophisticated architectural traditions long before the Inca Empire. And they tell us that a great deal of practical knowledge disappeared when the social systems supporting those traditions were disrupted. What they do not currently tell us is that the Inca possessed electrically powered saws, high-speed drills, advanced industrial grinders, or a demonstrated chemical process for turning massive hard rock blocks into something mouldable. Those ideas remain interesting hypotheses only where specific evidence can support them. The appearance of a stone is not enough. Perhaps the most reasonable conclusion is that the mystery is real, but slightly different from the one we began with. We are probably not looking at evidence of machines more advanced than archaeology allows. We are looking at evidence of techniques more developed than most modern people intuitively imagine simple tools can support. Some procedures may indeed be completely lost. Others have been partly reconstructed. Some probably survive in traditional stoneworking practices elsewhere, and some details may continue to puzzle us simply because the evidence required to recover them disappeared centuries ago. That answer may feel less dramatic than discovering an ancient machine beneath Cusco, but it gives us something more useful. It lets the walls remain extraordinary, without turning their builders into people who could only have succeeded through technology for which no physical evidence survives. The impressive thing about Sacsayhuamán is not that its builders somehow escaped the limitations of stone, gravity, friction, and human muscle. It is that they worked within those limitations so effectively. The impressive thing about Ollantaytambo is not merely that enormous blocks reach the temple area, but that the landscape preserves enough unfinished evidence for us to trace parts of their difficult journey. The impressive thing about Machu Picchu is not only the elegant masonry, but that the entire settlement was engineered to survive rain, slopes, drainage problems, and an unforgiving mountain environment. The impressive thing about the older Andean tradition is not that it supplies us with a convenient vanished super-civilization, but that it shows generations of experimentation existed before the Inca ever became an empire. And perhaps that is why these stones remain so effective at making us stop and stare. They sit at an uncomfortable distance from our own experience. They are close enough that we understand what a wall is, but unfamiliar enough that the process behind it is difficult to imagine. We can see the result clearly while the labour has disappeared. The gaps invite stories, and some of those stories become far more elaborate than the evidence requires. That does not mean we should stop asking difficult questions. Quite the opposite. We should measure the grooves, analyse the surfaces, test the abrasives, reconstruct the transport, examine the quarries, study older Andean sites, look for chemical changes where stone softening is proposed, build experimental walls and see which techniques actually work. The difference is that a good mystery becomes more interesting when every possible answer is held to the same standard of evidence. If a lost tool is eventually discovered, then we should change the story. If chemical analysis demonstrates an ancient process nobody expected, then we should change the story. If secure dating shows that a famous wall predates the Inca by centuries, then we should change the story. That is what makes archaeology interesting. The stones are not there to defend our favourite theory, they simply remain where the builders left them, waiting for us to ask better questions. After everything we've looked at, I think the most remarkable possibility is also the most human one. Perhaps the Inca did possess knowledge that we no longer fully understand, but that knowledge did not need to resemble our machines. It may have consisted of hundreds of small techniques accumulated across generations: how to choose the right boulder, how to recognise the beginning of a fracture, how to organise a pulling team, how to use a neighbouring stone as a template, how to grind away the last stubborn high point, how to drain a terrace before the rainy season, and how to train the next mason well enough that none of those decisions had to be written down. When that chain of teaching was broken, the stones stayed behind. And now, several centuries later, we stand beside them with steel tools, computer models, high-resolution scanners, and a great deal of confidence, occasionally wondering how people carrying what look like simple rocks managed to create something we would still find extremely difficult to reproduce. Maybe that is the useful question to leave with tonight. Not whether the Inca secretly possessed our technology, but whether we have become so accustomed to machines that we underestimate what human beings can do without them. So wherever you're listening from, take one last look in your mind at those enormous walls above Cusco, the unfinished stones along the route to Ollantaytambo, and the carefully engineered ridge of Machu Picchu. Somewhere behind every one of them were real people working, measuring, correcting mistakes, pulling ropes, choosing stone, passing down skills, and probably having disagreements about whether the block needed another little adjustment after everyone else was quite ready to go home. If you've enjoyed this quiet investigation into what the Inca may have known, you can give the video a like and subscribe to Just About Earth, and I'd love to know what you think after looking at the evidence. Do these monuments suggest a genuinely lost technology, a forgotten collection of specialist techniques, or simply a level of traditional craftsmanship and organisation that modern people find difficult to imagine? Whatever the answer eventually turns out to be, the walls are still there, the quarries are still there, and there is still more to learn from them. For tonight, though, we can leave the masons to their stones, the archaeologists to their measurements, and those giant blocks exactly where they have been sitting for centuries.